It's been too long.
Okay, got it.
We'll have to say got it. Okay, I think it's now 7:30 over here in Seattle. So let's get started. Good morning. It's 7:30 here in Seattle. I'm in Seattle. For many of you, it's probably like maybe it's afternoon or evening. So really thanks to everyone for attending this workshop. Multi-camera tracking actually is such a fundamental problem in many industry applications, but there is a really serious data shortage problem. That's what I see when I try to deliver products to customers. We need a multi-camera tracking, but there's such a shortage of data. So actually, I was wondering why. I think the multiple factors, probably because maybe privacy issue, maybe labeling difficulty. I mean, there are all kinds of factors, the potential factors, but we don't really know for sure. We're going to have some discussions on this topic later in the panel. So this lack of data, so there's a shortage of data, is really the motivation for our effort, sort of to collect some data, and also to organize this challenge and also this workshop. So the hope is that we'd like to use this forum sort of to encourage more researchers, like all of you, or all the researchers, to collect sort of multi-camera tracking data, and also to really share with the research community. In this way, sort of we grow the data, so then the field will keep growing and also advancing, so that multi-camera tracking eventually will become a really commonly used tool. That's what I really want to see. Really a common used tool for many real world problems. I mean, that would be really, really great. So I'd like to thank our advisors for their support and advice for the data collection and this challenge organization. And also I'd like to thank all the challenge participants. Actually, there are many participants that actually downloaded the data set. They might have tried it, but they might not have submitted the results to leaderboard. But we'd like to thank all of them for using it, for trying it. And I think there's really community effort to push it forward. Okay, so this is really the end of my short opening remarks. Next is our first keynote speech by Dr. Mubarak Shah. I will say a few words to introduce Dr. Mubarak Shah. I have known Mubarak for many years. He's a pioneer in computer vision and has done a lot of influential work in tracking, action recognition, among other things. Many of us, definitely including myself, have used, for example, like UCF 101, which was actually the work of Dr. Shah. He has many other works I've followed as well. This is just one example. Dr. Shah is really a role model and inspiration to many of us, including myself, many of our researchers in computer vision. Well, Dr. Shah is a general chair for the upcoming CVPR 2022. We were just chatting that he might, he wants to encourage people to attend, hopefully to attend the conference in person. Maybe that will become the first computer vision conference in person since the pandemic. Dr. Shah has won many prestigious awards. I will not enumerate them here just because it would take too long. There's many prestigious awards, just amazing. So without further ado, let's welcome Professor Shah.
Okay, so now you can stop sharing, then let me share this link. Okay, can you guys see it now?
Yeah.
Okay, so how do I? No. Okay, so I think part of my thing is missing here, but maybe.
Oh.
Yeah, I see you. So, okay, maybe that's fine. I think we'll start here.
Okay.
Okay, well, yeah. So, thank you for inviting me. I'm pleased to be here, and trekking is my favorite topic. I've been working on this topic for a long time. So the title of my talk is the multi-object tracking and multi-camera tracking, just to stay with the title of the workshop. So I'm going to talk about these two topics. And so let's get started, multi-object tracking. So this is like a traditional formulation of the multi-object tracking. So we have here detection of objects, and then we have data association. We will come out tracks. So now data association involves actually feature extraction, then affinity matrix computation, and then optimization. So detection in the old days, we used to just do this detection of the points, objects. It was mainly manual detection, single point on a person or person's head or whole body or joints and so on. But then these automatic methods came in, DPM, YOLO, and heat map based methods. So you can do this detection automatically. Now, features were also like handcrafted features like intensity, gradient, histograms, backup words, and so on. So the main work, the focus was in those days that how do we compute these affinity matrix? And we used to involve these different constraints like appearance, motion, and grouping constraint, and so on. And that once you get an affinity matrix, then you can solve this correspondence problem. So now this can be done using only 2 frames, which is called bipartite matching, 2 consecutive frames. Like here we have 3 and 4th frame, or it can be done multiple frames, which has advantages that you can deal with occlusion and appearing and disappearing of objects, like that. And there was a lot of work, including we did a lot of work on this area. So now to solve this association problem, given the affinity matrix, then you can use Hungarian method for bipartite graph matching. You can use linear programming. If you have multiple frames, you can formulate it as a network flow program. And then, there were lots of interesting methods. So emphasis used to be on the optimization method, coming with the different constraints and so on. So then a deep learning came in, and so people started using, so let's, instead of using these handcrafted features, we can use these CNN features. Take the pre-trained ImageNet model and get the features and get affinity, and then do this Hungarian and all other methods. So now what the question is that, well, can we actually end-to-end learn the affinity matrix, not just features from pre-train and then affinity? So that's the topic I want to talk about. And so in this one, we have feature extraction and affinity are learned together, because in the previously features separate and then affinity. So we have this nice paper in PEMI. It's called Deep Affinity Network for Multiple Object Tracking. So I'm going to talk about that. We call it DANE. So it learns these compact features of object with several levels of abstraction, and it performs extensive pairing of permutation of features and accounts for multiple objects appearing, disappearing. So it has these 2 parts. So this is first pass, which is for feature extraction. So we have this pair of frames and object centers, and we pass through these shared weight streams of convolution layers, and we get these features. And then we have these affinity estimator, which encodes affinity between the objects using their extracted features. So the network looks like this, and in detail. So we start with, say, first frame, and it centers. So we go through the VGG. So we look at these layer 16, 23, and 36. We get these features. And then we have these feature reduction, dimension reduction. From 256, we get 60. And from 2512, we get 80, and so on. Now, around each center of the object, we take the feature vector like this, and we flatten, we put it here. This is one object, second object, and so on. And we do this for all these layers. And we do the same thing for the second image, and we get these concatenation of features. In addition to these VGG, we have these extra 5, 6 layers here. And that also we do the feature reduction, we get these more features. So that's why it's different level of hierarchy, we have these features. So altogether, we get these features and get about 520 dimensional feature vector for each object. And then we do this pairing. So we take, say, object 1 from first frame, and we pair it with the object 1 from first frame, and object 1, 2 from first frame, 3 frame, and we get this whole row. Then we get a second object. Again, we pair with all these, we get second row, and so on. So we get this tensor, and then we have additional 5, 6 layers here, and then output the affinity matrix. Okay, so we have these 3. So to deal with the entry exits, we introduce additional row and additional column in this upstairs, the A1 and A2. So, so we have these losses. So one is the forward loss, which is this is the ground truth affinity matrix, and this is computed. So we just multiply these, had a multiplication, add them up. And this is for backward. And this is for the consistency, because as I said, A1 is we remove the row, and A2 is remove the column, and we want to make sure they're consistent. And this is for non-maximal separation. Just to give a little more detail about the data association matrix. So let's say we have 2 frames, frame 1, frame 30, and these are the patches. Now, since the objects, numbers, here we have 4, and then we have enter 5th object here, and actually 4 objects not here. So we'll treat these a constant number of objects, maximum number of objects which can appear. So that's why we have this 5 by 5 matrix here. And now this one is extra, the X, and to make it, 5 objects in both frames. And then we additionally have another dummy row and column to do this entry exits. So doing that, then, this works pretty well. These are results for mode 17. We get pretty good results at that time when we published the paper. This is on mode 15. And we also apply on this vehicle tracking data set. This is called D-Track, and on that also works pretty well. So these are some of the results. And you see that pretty crowded scenes, and the are constantly matched. It's a pretty long sequence here, so I'll just show you little snippets and like that. So this was about the mode, and then this is about the vehicles that are said. So you have bus here, the truck, and things like that. And it is a pretty nice method with the good results. So in summary, we have this end-to-end learning of affinity matrix, and learns compact features of objects at several levels, and perform exhaustive pairing of permutational features, and account for multiple objects appearing, disappearing. Now, so this was 2D tracking, and most of the work has been in 2D tracking. We have these regular RGB videos. Now, what's becoming more important is the 3D tracking, which is in context of self-driving car, robot navigation, and so on. So also, LiDAR captures the 3D information in terms of point clouds. And now, of course, the 3D is better than 2D because it captures the structural information or the perspective distortion. And also LiDAR is widely available now. Even on my iPhone, I have a LiDAR, iPad has LiDAR, and so on. So we extended this work to the 3D tracking. We call it PC-DEN, which is like point cloud DEN. And actually, this summer, we entered this competition in CVPR, which was the organized by this dataset. They collected new dataset GRDP, and actually this entry one was at the top of the leaderboard. So PC-DEN. So now we are going to look at the 3D bounding boxes detection, and that was done by PointNet. And now, as I explained earlier, that we were looking at the whole image features, then we were extracting around the center of each object, these feature 520 dimensional feature vector. But now this 3D LiDAR data is very high dimensional. So we actually process one object at a time and sort of whole frame. And so we have, say, NM objects, and then these are represented by 3D points. We have P points for each object. And so we aggregate these features by average pooling for all these, and we get this 512 dimensional global descriptor for each object. And then we have to, when we implement this, so we have to, we were not able to use this batch size of reasonable size. So we have to do the group normalization to, to increase the batch size, and works pretty well. And it also reduces the training time. So it looks like this. So we have the frame T and frame T minus 1. We get the 3D point clouds, and these are different objects. So each object has this set of 3D points, and we go through this point net, and they are shared for frame T and T minus 1. And we repeat the same process, get these feature vector, concurrential feature vector, different layers, and then do the pairing, and then, do these 3 losses exactly same as we did before. And we apply this on 2 datasets, Kitty, which is the front view autonomous driving scenario, and then GRDB, which is 360-degree view, indoors and outdoors. And both of them use this Velodyne, LiDAR. Now in Kitty, it's just single LiDAR, and in GRDB, actually they have two LiDARs, and so that's why it's captured the 360 degrees. And it was a big issue students had to take those 2 views and stick together using calibration and so on. So we have the number of objects now. It varies. The Kitty had about 15 cars maximum objects and 30 pedestrian, but the GRDB has about 200 people. So it was a pretty big data set. So we have to adjust that. And then now the detections, they were available as public detection, but when we use the private detection by this method, we can actually increase the performance by about 14%. And similarly, we had a big problem with the provided public detections from GRDB. We had to apply some threshold to remove some of those. So, so these are the kind of examples of indoor. So as you see, these are the 3D bounding boxes. This is the camera view, and this is the outdoor data. So these are the point cloud here. So this is the result on Kitty. So we do pretty well, competitive to, this was the best on 83, we get about 81. Now this is what when you use these private detections, but if you use the public detection, the actually performance go down because the detection is a problem. And GRDB, we were at the top, and we did pretty well compared to these two other submissions. So, and these are the qualitative results for the car data set, for the kitty, and this is the results for pedestrian. As you see, there are quite a few people crossing each other and so on. So it works pretty well. So in summary, we extended the DEN to PC DEN and PointNet instead of VGG for feature extraction, and process objects instead of frames due to the data size. And we got the state-of-art results on GRDB, comparative results on Kitty. So now going back to these formulation of object detection, we talk about, you have detection, and then you do feature extraction, affinity matrix computation, you learn this, and then you do this Hungarian, whatever you want to do here. Now, other interesting thing here can be that we can actually do detection, feature extraction, affinity matrix computation together. So that's another end-to-end learning as compared to relying on detection. As I mentioned, the detection, if they are not good, then performance goes down on tracking. So actually, we had a nice paper last ECCV about that, which is simultaneous detection and tracking for multi-object tracking. So I won't have time to talk about that, but essentially, it's takes a bunch of frames and it's kind of extension of SSD, which is for object detection. This is for the tube detection, and within that we have these set of tracks, and we estimate the motion, what class it is, and also visibility. And we apply this to actually MOT and also the vehicle tracking. Now, the problem with vehicle tracking is that there's not any good data set. So we actually generated this synthetic data set using this Carla simulator. So there are 5 cities, 39 cameras, and different easy view, ordinary view, and hard view. And there were about 90 videos and lots of frames. And so this is a pretty nice data set. And this is some demo of that. It's a pretty long video, so you can see different views. These are all synthetic. It looks pretty real here. So these are the cars here, and there's some different cities, and there's a nice outdoor thing, mountains here. So I was thinking that, as was mentioned earlier, that big problem multi-object and multi-camera tracking is the data set. So maybe using some synthetic data set may be, I think, one way to get out of that. And this method works pretty well for the simultaneous detection and tracking. This is the results on the D-track data set, and these are our Omni data set, which was a synthetic data set. Okay, so I'm done with the multi-object tracking. Now let me go to multi-camera tracking. So now if you look at tracking in general, so what we have been talking about is the stationary camera. There's one camera and it's stationary, and there's a lot of work on that. MOT is on that, multi-object tracking mostly. But if you extend this, now you can use multiple camera with overlapping field of view, because if you want to cover a large area, one camera field of view is not enough. But if you don't have many cameras, actually you'll have a non-overlapping field of view with multiple camera. And so then another configuration is that you want to do tracking in a single camera, but it's a moving camera. And then you can have multiple moving cameras with overlapping field of view and multiple moving camera with non-overlapping field of view. So actually, we have worked in all these areas, started a long time ago. So this was our first work here, that we wanted to cover a whole room with 3 cameras. And so problem is that, when we do the tracking, so you have to assign a consistent label of the people you are tracking in all the cameras. And so that problem is called handover problem. So the way we did this, that we have these edge of field of view lines we calibrated, so that when the person appear in red camera, so he will cross this red line which is visible in the blue camera. Similarly, this edge of field of view of the green camera visible in the blue camera. So like that, we have lines, then we can assign these labels pretty easily. So we have here person once appear here, assign new label. He crosses red line, he'll appear here, assign same label, and then crosses green one, assign same label. So there's second person, we assign new label. The third person assigned third label, it crosses red line, green line, and so on. So then he's going to walk, the red one's going to walk again. So we now have the overlapping field of view, multiple camera tracking, and consistent labeling. So the next thing we worked on was the non-overlapping field of view. So we have here 3 cameras. So this is the field of view, 1 camera, the second one, and third one, and there's no overlap. And it's a pretty complex problem. So here, so first person enters, assigned first label, then this is indoor, and the other 2 are outdoors. The second person appear here, assign new label, third person. Then, after some time, they will go out and appear one of these outdoor cameras. And the challenge is to assign the same label. So again, see this same guy is assigned label 1. And then we will have another person appearing from other cameras, a field of view. Again, we want to assign the same label as we assigned. So here, assign same label 2, and another 4th guy come in, 3rd guy. So that was pretty nice. We had a paper in ICCV 2003. And so now we can also do the moving objects and moving cameras. So these are the animation that can we do the multiple camera tracking like that. So here we use this epipolar geometry idea. So suppose there's an object moving in 3D, and these cameras are also moving 3D. So what interesting thing is that you can actually define this epipolar geometry, which we call this temporal fundamental matrix. So the idea is that if you take these corresponding points between 2 sequences, and they are independently moving cameras, then that can be related with this fundamental matrix. And then using this, you can actually do the tracking. So here, as you see, that this blue person the same here, and the red person here is same, even though the trajectories look very different because of this constraint we are using. So so now right now what we have, that typical approach for multiple camera tracking is that we assume tracking in individual camera is solved. Then we want to solve the handover problem or re-identification or track correspondence across the cameras. And that's what I've been talking about in these different methods. So now I want to end my talk talking about this new approach that will simultaneously solve the single camera and multiple camera tracking in a single framework. Okay, and also this can also be used the video person re-ID problem, because person re-ID problem is very hot area, but video person ID is actually more interesting, and that can relate actually to the tracking. So which is pretty interesting here. So this is a paper we had in IJCV, and we are using this what's called the constraint dominant set idea to solve this problem. So we have these two parts. So within camera tracking, so let's say we have 3 cameras here, and these are the tracks. So subscript represent the camera and superscript represent the objects. So we have 4 objects here, 3 objects here, and so on. Then we will take those tracks, and each of this will become a node in this graph, and then we will have the across camera tracking. So, so the pipeline is we have n cameras, we do the human detection, and then from there we get these short tracklets, and then now we make this k-partite graph, and each of the short tracklet become a node in this graph, and apply this constraint dominant set to get tracklets. Then we have a second layer where the nodes now are tracklets, and we want to apply another constraint dominant set to get the tracks. And then we have a third layer where we will have these tracks as a node from different cameras, and we will apply third layer constraint dominant set to get the across camera tracking. So that's the way it works. So let's look at the first layer. So, same process, human detection and data association. And what we are going to do is get this human detection, and then we will just get the short tracklet just overlapping constraint, whichever is closest, we say they correspond. Then we apply the constraint dominant set to stitch these short tracklets to get the tracklets, and then finally we get the final tracks, second layer of the constraint dominant set. So, so let's look at how we do this first layer. So these short tracklets are 15 frames long. So we have these short tracklets, and the first 15 frames, another 15 frames, and so on. So we make this the k-partite graph. So we connect these will become nodes, and we connect them to all others, completely connected graph here. And so now on this one, we will find out the consistent dominant set or cluster. So maybe first cluster will be actually give us the tracklet of the one person. Then second cluster will be tracklet of another person. And we can keep repeating. And that's the way we are going to get these tracklets. And so then second layer, now the nodes will become the tracklets, and we want to get the tracks. And so that is another data association problem. Nodes become tracklets, and CDSC is used to stitch tracklets. And so then we have the third layer. So we repeat the same process. So let me say a little bit about dominant set. So dominant set is age-weighted generalization of clique, and it is a subset of vertices which is coherent and compact. And so this is an example of dominant set, with 3 nodes, and this is a similarity between node 1 and 2, and similarity between 2 and 3. So this is coherent, and this is dominant set. Now we add another node 4, and again the similarity of 4 with 1 is 40. 4 with 3 is 41. So again, this is a dominant set. Now, when we add the 5th node, now their similarity is very different from these ones. And so this is not a dominant set. So formally, this is the age-weighted generalization of maximum clique. And we are given the affinity matrix A. And so we want to maximize this cost function, X transpose AX. And so X is simplex. So we just give you a membership of each element in the set. And this has to be summed to 1 and a positive. And so once we can find the maximum of this, then the support vector of that is actually dominant set, and which is internally and externally coherent condition for a cluster. So now we have notion of this constraint dominant set. So here, what the idea is that we will have a constraint. We want to find a set which is dominant, but it contains the constraint. So we want to have this 8 as a solution in this constraint dominant. So this will be one constraint dominant set, and this will be another constraint dominant set, because each of these contain the 8, node 8. So that also we can find very similarly as we find the dominant set. The only thing is we have to change this. They introduce this diagonal matrix S. So this contains the constraints, and the way we are going to do is in that diagonal matrix, we'll have 1 for all the vertices which are V minus S and 0 otherwise, then the same process. So this works pretty well. So let me now explain a little bit more how we do this cross-camera track association. So let's say we have 3 cameras, and let's say we already found these tracks for in camera 1. So these are all the tracks 1, 2, 3, 4, camera 1. These are the tracks in camera 2 and camera 3. Now each of the track becomes a node in this graph like this, and we also want to connect these nodes within these camera also. Okay, so then we apply the constraint amino set. Let's say we say camera 1 is a constraint now. So we want to find our dominant set which contain some of these nodes here. So maybe the first constraint dominant set is here. So now this gives you actually a cross camera tracking, because it's saying this track, this person in camera 1 is the same, actually this person in camera 3 and this person in camera 2, the track of that. And also saying that actually this track of this person was broken, and so we can connect that. So which is pretty interesting. So this will be the first dominant set. And then we can get another one. Now here, this track is broken in camera 3, so we can actually connect it also by leveraging these multiple camera correspondences. So we get track here, set here, and like we can get a singleton here. So that is when camera 1 was a constraint. Now we can use the camera 2 as a constraint, and we can repeat this, and then camera 3 as a constraint. So we'll get these kind of constraint sets, and then we have to assimilate all those to come up with the final tracks. So we have this constraint that we want to make it at most a track should be member of only one dominant set, one camera. Second is that maximum number of sets that contain tracks should be equal to number of cameras under consideration, which makes sense also. So doing all that, so we get pretty good results. We apply this on the Duke dataset. So this is a pretty large dataset, and unfortunately it's not available now. But so it has this overlapping field of view here and this non-overlapping field of view. So 8 fixed camera, about 50 people per frame, about 3,000 identities and so on. So here are some examples. So we have camera 5, camera 2, and camera 7, and camera 4. You see that here the person 714 appears in camera 4, and then it exited from here, then appears camera 7. It enters here and then goes like that. Then it enters here camera 5 and then exited here. So in all these, we have the same ID 714, and that is the multi-camera tracking. Okay. So then we have another example, this 238. So enters here and then exited from here, then camera 2 enters here. Look very different. These are different viewpoints, as you see. Then enter camera 5, and then exited here, and so on. So there's another example. Look at 212, enters like this, and then enters camera 1 like that, and then camera 2, and then camera 5. So it's pretty interesting. You can have these consistent ID, and that's the whole idea of multiple camera tracking. So these are the videos here. So look at the 371. So this guy is going here, and then he will appear in this camera. You are tracking him, and then he will, after that, he will appear here, camera 2. So that's the Duke dataset. So the performance were good. These are the metrics. And so first is we want to check the within camera tracking. And at that time when we did that, there was only one method. So we do pretty well. So mostly it's mode A. And this is the hard case. Again, we do pretty well. And this is about the multiple camera tracking. And this is test easy, and this is the test hard. You do significantly better than other method. Now, before I end, so one thing is that this the re-ID problem actually is also a sub-problem of multi-camera tracking. So if you want to do video-based person re-ID, so what you have, we have input clip like this, and you have a gallery like this. So traditional method will focus on build better features, build a better distance metric, and then finally you rank the images or video from the gallery based on that distance. So we can apply the same method I talk about the multiple camera tracking to person re-ID. So we use the standard features and distance metric, extract the consent amino set for each query, and perform tracking over shortlisted clips. So the advantages are that we are taking account relationship between the query and elements in the gallery and elements in gallery. So here is the example. So we have input clip, and this is a gallery. Okay. So we again make this graph, and then these are the the gallery clip, and this is a query, and query is a constraint. So we want to find our consent dominant set from here, and this is the one which should include a query, and then we can actually get the re-ID. So we apply this on Morse dataset, which has 6 synchronized cameras, about 1200 IDs, some distractor, and so suppose if this is a query, then first nearest neighbor is correct, second nearest is correct, and third one's incorrect, then fourth one is correct, and like here, first 3 are correct, and so on. As you see, there's a lot of change of these viewpoints. So still we are able to recover this. And some more examples. Here we get all correct. Again, this looks very different than the actual gallery. This is completely different viewpoint compared to this one. And so on. So we get, pretty good results compared to these other methods. Okay, so just summarize that I talk about a single framework for multi-target tracking multiple non-overlapping cameras. There were 3 layers of hierarchical approach, 2 layers for within camera, and 3rd layer across camera. And then we can apply the same method to solve the video re-ID in multiple cameras. And we got the state of art results. and we applied the on two dataset, Duke dataset and the Morse dataset. So this is the, just to summarize the whole talk, I started talking about multiple object tracking and talk about the detection and data association paradigm. Then propose this method, deep affinity network for 2D tracking, which computes the features which are useful for the affinity matrix computation. And then we extended that to point cloud then for the 3D tracking LiDAR data set. And then talk about the multi-camera tracking and went through different configuration of general tracking, like overlapping field of view and fixed camera, non-overlapping field of view, fixed camera, and then overlapping field of view, moving cameras, and non-overlapping field of view, moving cameras. Then talk about this our method, constraint dominant set based method to solve this multi-camera tracking problem. So thank you.
Thank you. Thanks for the nice talk. For people, if for the audience, if you want to ask questions, please you can either just directly turn on your microphone and talk, or you can enter your questions into the chat window. I will start with the first question. So you mentioned the synthetic data and also did some experiments on that. I was wondering about the semantic, sort of the gap between the synthetic data and the real data. I wonder if how do you see whether the method is sort of trained and tested on synthetic data that would be how well it will work and can be adapted to the real data? Could you comment on that?
Yeah. I think that's a pretty interesting question, and that used to be old question in computer vision. We used to think that synthetic data is pretty useless, and people used to kind of make fun of it. But see that with the deep learning based method, it's amazing that synthetic data actually works so well. And I think the problem is that for learning, you need lots of data, and it is not possible to get a lot of real data. So this is example that the reason multi-camera tracking is not that active, because there's not much data set, and it's good that you guys collected this data set. So I think the synthetic data set is pretty useful, and it actually works very close to as you have the real data. So we should do more of those, and that will actually reduce a lot of burden, because when it's a synthetic, you actually don't need annotations, right? So all the annotations are available. You have bounding boxes and so on. So that's a good direction to look into more.
Okay, thank you. Any questions from the audience?
Hi, Professor Xia.
Yeah, hi.
So it's very nice talk. In your method, you used the spatial and the temporal, relation across different cameras for the tracking.
Yes. So I talk about several things. So the last method was basically just using these features, and features were these CNN features and so on. So and it was at a hierarchical manner that first you solve the short tracklet, then tracklet, and then you have the cross camera. So so when we build this graph, so we just have these appearance features and then motion constraint that, we assume the constant motion, we get that. So temporal features are used in terms of the motion constraint. The previous, method we talk about, the traditionally, the temporal features have not been used in the tracking, right? Only constraint is that, how is the motion. But I think when you use the, instead of, actually interesting point, what you are making, that if you use like in this video-based EID, right? So you have a clip and you want to retrieve the similar clip from the gallery. So now there are different ways to do that. And the way I talk about it's, like using the tracking method to solve the ReID problem. So we were tracking objects and, and computing features and so on. And those features were 2D CNN. But here you can, also compute 3D features, And so that is, where you can include the temporal features. The other method, then I talk about that we have 2 frames and we compute the VGG features for each frames and do that. And that's a 2-frame affinity matrix. So there you cannot use 3D features. But in general, I think it'll be a good idea we should look into how the temporal features can be also applied in solving these problems.
Thank you, Ron.
Thank you. The time is over. So let's thank Dr. Xia again for the nice talk. Thank you.
Thank you.
Next, we'll introduce dataset. Introduce dataset and also make a winner announcement. Xiaotian, can you share your slides?
Yeah, I have already shared my screen.
Okay, yeah, please go ahead.
Okay. Hello everyone. I'm Xiaotian Han from Microsoft Azure Cognitive Service Computer Vision team. And I'm going to give you a short introduction about the multi-camera, multiple people tracking datasets and this challenge. Here's a basic statistics of our dataset. We record our dataset from 5 different indoor environments: retail, lobby, industry, cafe, and office. And we have deployed a different number of cameras in these environments. We split our dataset into training, validation, and the test set with approximately a ratio of 2 to 1 to 1. And we guarantee that the videos of each environment are also split with the same ratio. So when we train the model, we can at least guarantee the model can see each of these environments. And we also make sure that the person identifications are not overlapped in training, validation, and the test set, because we don't want model to overfit to the person's appearance feature. Our dataset has totally around 576 minutes of videos, 23 different camera views, and we also provide the camera calibration parameters. Compared with previously public available multi-camera tracking datasets, which are either relatively short or sparsely annotated, our dataset is largest multi-camera tracking dataset with densely annotations. We hope this release of datasets can help improve multi-camera tracking research community to develop new models and serve as a benchmark dataset. Here, let's look at 2 sample videos of our dataset. The left videos are for retail environment, and the right videos are for industry environment. For example, you can see from the retail environment, even though sometimes people are fully occluded or half occluded by the shelf, we still label their bounding box from foot to head. Yeah. Then I will talk briefly about the dataset collection procedure. We use totally 4 half-day to collect all videos. For each half-day, we hired 7 people to participate and ask these 7 people to act in all 5 different environments. For example, in retail environment, we ask them to push shopping cart, hold a shopping basket, hold product, standing in line, pretend to be checkout, abandon line, or talk with each other, something like that. And in industry environment, we ask them to work in different directions with different speed, hold boxes, hold ladders, etc. Yeah, and besides these script actions, we also ask the participant to act freely. We think this kind of actions can increase the randomness and the diversity of the data. Totally in our data set, we have 28 different person IDs. And when we hired people, we try to keep the fairness. For example, we hired similar numbers of people from white, black, and Asia, similar number of people from male and female, and from teenager to elder people. And during the whole data set collection procedure, we ask all participants to wear face masks. This is part of the due to COVID-19, and we also don't want this participant to leak their personal informations. Then I'm going to talk about our dataset labeling procedure. For each of the environments, we deployed several error connect. This type of camera can record RGB and depth images at the same time. Then we can reconstruct the complete 3D point cloud merged from different RGB and depth views. And then we apply our RGBD tracker and get a person's 3D bounding box in world coordinate and their corresponding IDs. And finally, we back project these 3D bounding boxes into camera views 2D image plane to get the final 2D bounding box. And after that, we will have human to verify and correct the errors during our RGBD tracker. So for this challenge, we set 2 tracks. For track 1, we evaluate tracking result from top-down view. For this track, participants need to use camera calibration parameters to map ground plane from each camera view into a shared world coordinate. And we provide ground truth person center coordinates in top-down view. We define ground truth and detected person center point as matched only if the distance between these two are less than 0.5 meters. And we average across all videos to get final MOT and IDF1. The final ranking is based primarily on MOTA. And if MOTA are the same, then we check IDF1. For track 2, it is evaluated on camera view directly. Following similar tradition of evaluation used in MOT challenge, we define detected bounding box and ground truth bounding box as matched only when IOU is bigger than 0.5. And we average results across all video clips to get the final metric. And the ranking is similar to track 1. Finally, I'm going to talk about some problems and lessons we learned and encountered during this challenge. The first thing we notice is that there exists bias in our dataset. Each video clips has exactly 7 person IDs. Because our dataset is recorded during the COVID-19 pandemic. So it is hard for us to hire too many people to participate in our dataset recording. And so in order to fully utilize those participants we found, so we asked them to participate in each recording sessions and trying to make the environment looks crowded. So this kind of dataset bias may lead to some extreme good performance if someone fixed the number of tracklets in their algorithm or use some extreme hyperparameters like extreme long life of tracklet to tune their algorithms. So we our solution is to we check the participants' code to make sure that no one's using utilize this kind of dataset bias. The second thing we noticed is that we didn't set any limitations about using extra data, model complexity, or use model ensemble, or use online or offline inference. So in our challenge leaderboard, we mixed all different methods together. Even some so this can lead to the problem that someone not willing to public their result because they can't beat the top ranks metric, even though they use some very innovation or creative methods. So in the future, we can definitely separate the leaderboard into different sessions, like if it is using extra data or not. Yeah, here's on my part, thanks. For next part, I will head over to Dr. Quanzhen Yu for winner announcement.
Okay, thank you. Yeah, Xiaojun, can you go to the next slide? Thank you. Okay, so maybe you go to the next one. So we have 2 tracks as mentioned by Xiaojun. So the first track is top-down view. Here we can see we have 4 teams from Alibaba, Hikvision Research Institute, USTC from China, and also Fujitsu Research. So as you can see, the number is pretty high. Congratulations to all the team. You know, they really achieve very good results in terms of the MOTA and the IDFY. So this top-down view, as mentioned by Xiaojian, probably are two reasons. And one is the data bias. The other, I think, is the evaluation metric we used because we focus on the horizontal plane, where the bounding box is fixed. But still, it's very exciting to see, you know, they achieve such a high, good results. So hopefully you can join us later to see how they can achieve those kind of good results. So congratulations to this 4 team. And also I want to mention the Hikvision, they also achieved #1 in the next track. Maybe it goes to the next slide. So in the second track is the camera view. And again, Hikvision ranked #1. And also with team AI, with lab AI team, they also achieve very good results. And also the information processing lab from UW. So I think, you know, as mentioned by Xiaojian, there are some data bias. So we are going to include, you know, more complicated backgrounds and change the number of people in each environment. So I think maybe in the future, people can focus on developing online or even real-time trackers so we can, you know, easily apply this technique to some real-world applications such as intelligent store. And so hopefully more research team will join us using this data set. So probably we are also going to review some more extra data for this challenge. Okay, thank you. Yeah, I think if you have any question, maybe you can ask us. If not, maybe we are running out of time. We can go to the next session.
Well, thanks, Chen. Yeah, it was a great challenge. I'm surprised to see such a great result. Even though the data sets will have some biases, but it's still really amazing to see the good results there. So next session is the panel. We're going to talk about discuss the ethics, privacy, and diversity issues in the people tracking. This is really a very, very important issue, and also it's sort of a difficult issue for us. I have invited 3 distinguished panelists: Dr. Houdong Hu, Professor Mingchuan Yang from UC Merced, and also Professor Haibin Lin from Stony Brook University. Thanks to the 3 panelists for joining us. So the format is that each panelist will just give a 3-minute, probably just a position statement, talking about their thoughts on this issue, and then we will move to QA. So I have prepared a few questions, but for the audience, if you have any questions, please submit your questions to the chat window. I will constantly check the chat window to see if there's any questions from the audience. Okay, with that, let's start with the position statements. So 3 panelists, Houdong, Mingchuan, and Haibin. Who do you want to go first to give a brief statement?
Hi, Zichen. I can go first, maybe.
Okay, go ahead, Houdong.
Yeah, so thanks for the introduction, Zichen. My name is Houdong, and it's my pleasure to be here to share my thoughts. I am an engineering manager in Azure Computer Vision team. People tracking is a high-value scenario that Azure Computer Vision team focuses on. And we have released the spatial analysis cloud service, which based on people tracking and helps organizations maximize the value of their physical spaces by understanding people's movements and presence within a given area. And there are broad real-world application opportunities for people tracking model. However, people tracking dataset as one type of biometric dataset is sensitive, since it could be used for the purpose of identification. I will briefly share my view on ethics, privacy, and diversity issues in people tracking dataset collection. The first issue is ethics. When our team collects people tracking dataset, we typically invite actors to an authorized space Let actors understand how the dataset will be used, for example, commercial purpose, and let them sign a data usage consent form before we start recording the dataset. Also, we invite actors targeting to a uniform distribution on ethnic groups, gender, etc. And before we release people tracking-based solution as a cloud service, a fairness test is required to make sure our solution performs equally well across different ethnic groups, gender, etc. The second issue is privacy. Face feature is most sensitive for the purpose of identification. Thus, in this released dataset, every actor is wearing a mask. Face blurring is another common de-identification process. And regarding the Azure Spatial Analysis Service, customers can only access the end-to-end insights, such as the non-crossing activity, but not the intermediate person feature embedding vector, so which minimize the privacy risk. The third issue is diversity. Due to high annotation cost and lack of data resources, there is a lack of large-scale diversified people tracking dataset. The dataset released in this workshop is annotated through the auto-annotation system using RGBD people tracking inference results, and the project back to RGB camera view as pseudo-bound truth, which is a novel approach to solve the data annotation cost issue. If we can deploy this auto-annotation system to several diversified environments with consent form from both space and people present in the space, this can lead to a diversified RGB tracking dataset, and it's our hope in long term. So in summary, although there are also challenges in people tracking dataset, we as a community achieved great progress in the past years. The multi-camera people tracking dataset we released in this workshop is a great example on this. And that's what I want to share today. Thank you.
Okay. Thanks, Hodong. Who want to go next? Min-Chuan, you want to go next? You're muted, Min-Chuan.
Let Haibin go first.
Haibin go first.
I don't have a statement. I mean, I can just briefly say something. I don't prepare a slide, but Haibin.
Just say a few words.
Me?
So Haibin, you want to go next? Because Min-Chuan wants to think about it a little bit.
Well, I can say something. Yeah, I think that the problems are important, and certainly, yeah, we just have a few data set available, right? So, you know, in the old days, even for single object tracking, we have to collect our data set on our own, but that is easier. For multiple people tracking, you need to have a larger environment, and you need to have a different camera setup. So there were several projects on that, and certainly the dataset released by this workshop makes good progress. And as far as I know, there is a IAPA project that will create more datasets along this line of work. But that probably will come out in 1 year or two. And yeah, so, you know, these are important issues, and you know, but if you put a camera out there and then you certainly cannot put the camera on campus without permission. And of course, when you say deburring and all that, they help, but you know, administration usually would tend not to allow this because nobody wants trouble, so nobody wants lawsuits. So yeah, but in order to make progress along this, then certainly some people need to create a larger data set. So and yeah, for diversity, that is if it's very challenging problem, because this is just the way it is. It's very difficult to have a balanced data set. We can try to do that a little bit, but this is certainly a much more difficult problem than privacy or ethics, I would say. That's all I have.
Okay, thank you. Thanks, Min-Chuan. Haibin, let's say a few words.
Hi, yeah, thanks for inviting me to the panel. Okay. Yeah, I think in general I agree with Mingshan's point. So it is very difficult, very challenging. So I'm glad that this workshop addresses these tough issues, and I think very thoroughly and with full consideration. Yeah, with respect to my own experience, yeah, my group we did kind of compiled. Remember, I didn't use the term collect. We did compiled a few benchmarks for tracking, but these benchmarks we collected are for generic object tracking. So mostly we collect videos from the internet. We did put quite some effort for diversity, but that diversity is for category level. So basically, we wanted the tracking evaluation to be kind of fair for different categories, like common categories like cars, and uncommon categories like some special type of animals. In this sense, I think technical-wise, in some sense, a little bit similar to the diversity for people tracking, because we also want the algorithm to be relatively fair for different subcategories of humans. Yeah, but regarding to people tracking, first of all, we don't have much experience in collecting such data. But I totally agree with Mingshan's point. It's very difficult because maybe especially for universities, because it's really hard for us to, with limited resources and funding, it's hard for us to rigorously collect a large amount of data set and people data set with consideration of diversity and the privacy or kind of issues. Yeah, and another thing is I kind of we also did some work on kind of privacy related face de-identification and the license plate de-identification. But during that research, we realized one issue. So you know that for human de-identification, even if you kind of blurred my face very often, you can still recognize me, and by my maybe hairstyle or by my the clothes I typically wear, or even by the background. Okay. So should we take consideration of these issues or not? So yeah, that maybe we don't need to take consideration now, because those algorithms are not robust enough now, but in the future we don't know. So I think these are really open issues and open problems, and I'm really glad that we have a chance to discuss about this. Yeah. So those are my questions.
Okay, thank you. Okay, so yeah, now let's move to the Q&A. Again, so if you have any questions, please submit to the chat window. I like to really, I think it's, since we have other people here, so it's good to have some discussions on this topic. So I will start with the first question. Again, since it's so difficult to collect the real data, I wonder, so what's your view on synthetic data? Shall we, as a research community, shall we focus more on developing techniques to generate useful synthetic data? Because the end of the goal is still make it work on the real data, right? So yeah, so this topic is really about how to, what is possible, or how to leverage synthetic data so that can be useful for real data. I'd like to get your thoughts on this. Yeah, so that's the question. So who wants to go first?
Yeah, I can go first.
Okay.
Yeah, I think given the challenge and difficulty we just discussed, synthetic data might be, at least at this stage, might be the most realistic solutions for this moment. Okay. And also, synthetic data have gained quite success other or related topics. So I think it's good to have a synthetic data relatively easily address all these issues.
Yeah, I agree. I mean, just at this you can use GAN, and you can make it as realistic as possible. And for the time being, that will be a good direction to go. And in addition, it's easier to collect larger data set than any human can collect, right? So, and you can also swap. You can also do some tricks so that you can reduce the privacy issue. So, I mean, to the minimum. So certainly that's a good direction to go.
Yeah, so I totally agree. Yeah, you can solve both privacy concern and also and the data annotation cost concern. Yeah, thank you.
So what about the do you feel like the a model trained on synthetics data would work well on the real data? For some other fields, I mean, this so far is sort of in some problems seems to be working pretty well. For some computer vision problems, doesn't seem to work well, at least not yet. But for tracking, I have not seen many like between synthetic and real. I'm talking about the sort of the sort of an adaptation from synthetic to real, right? So I wonder, maybe just I haven't done so much work. Maybe you guys have more experience. I wonder if you comment on that, like how do you think of the sort of adaptation from the synthetic to the real data? Do you think that's it's easier compared to other problems? So maybe the domain gap is not as big an issue for tracking, or yeah, I just wonder could get your thoughts on, because we do have some synthetic data. Actually, we're thinking about maybe adding some synthetic data in the future in the next challenge. We have actually quite a bit of them. We can generate more because it's synthetic. Yeah, I think it would be good to get your guys' thoughts on to see how the synthetic data can potentially benefit the real data, so tracking problem.
Yeah, so I can maybe try to share some our experience. So at Microsoft, when we are trying synthetic data, we find that synthetic data works better for tracking or real ID. So this scenario, because focus on the difference among frames. So this reduces the requirement of the domain gap between the real data and the synthetic data. But the synthetic data works not so good on the recognition task, because you really need the very realistic data set. That is one finding. And another thing we find that is pretty interesting, that in the research community, we see people now try to combine the synthetic data generation with the end-to-end task optimization together. So not treat them as two separate steps. So by that way, potentially you can generate the synthetic data more targeted for the end-to-end task. Yeah.
Well, thank you. Any thoughts from Haibin Minchang?
Yeah, I think this might be related to one thing is, I mean, when we want to address the privacy and the diversity and all kinds of issues, so which may actually make a gap between the public benchmark and the real application, because in real application we usually we kind of want to work on real data, but those data may not be used for public benchmarking thing. Okay, so then how to do the domain adaptation might be another issue. In other words, they best perform the tracking algorithm on a benchmark. A benchmark which considers all these ethic and the diversity issues may not be the best. In practice, especially for specific applications, maybe for example for surveillance videos, just for example. So then there is a kind of a domain adaptation issue. Similar thing happened for using synthetic data to real data. Yeah.
Thanks.
Yeah, I think certainly this will be useful. The only thing that if you use low-res image, then I think synthetic data will be as good as real one, but for high-res image, because of sensor, because camera, and then you have different characteristics. So then the synthesized data usually looks sharper than the real ones. So that may be the problem, because if you train on such clean data set, then when you apply to real situation, even if you use domain adaptation and like, the result will still not be as good as you train on real data sets. So certainly, yeah, I mean, it's a good way to go, and we'll get there with with everyone chipping, with more people working along this direction. Certainly, we'll get there.
Right? Thank you.
Maybe one solution is, I mean, when
Yeah.
we present some synthetic data, I mean, maybe we should come together with kind of a small amount of real data, and especially for testing one. So instead of just publishing synthetic data.
That's similar to yeah. There are a lot of it's not related, but there are a lot of work on supervised learning or self-supervised learning methods, and then when you apply to downstream task, you do need to train on some small real data set. Yeah, you're right. I mean, I agree.
That's interesting. Maybe we can, in the next challenge, we can have a track where the training is synthetic data, but we can add some small amount of real data without labels, for example, and then the test will be real data. You think that would could make an interesting challenge? So encouraging people to explore leveraging synthetic data.
Yeah, I think that's a good idea. I like that.
Thank you. Okay, so next question. I see that. I mean, so we all know that there are so many cameras installed in the public space, like on the streets, in the public squares. Like in New York City, there's just so many cameras. I sometimes enjoy looking at them. Some of the cameras, some of the footages from like Times Square. There's so many cameras. Are really quite dense. There's not much overlap, but it's not that far from each other. Certainly, you can apply like the methods that Dr. Xia just presented to those footages. I mean, yeah, it actually could work. So I was wondering, it's possible that I wonder if people will find a way, somehow will find a way sort of to address the privacy issue so that like the data captured by those cameras in the public space can be used by researchers to advance the field. So right now, I feel like the main reason, that's my guess, I'm not really sure. My guess is that we're not using those is because of the privacy issue, I suppose. Maybe there's some other issues that I'm not aware of. Yeah, I like to, seems like those are really, really good data, right? So because the people move around, it's a huge area. They cover so many streets, there are many cities. So anyway, so I'd like to get your thoughts on this kind of this interesting problem. I feel like this could potentially be a really, if we'll find a way to use those data, it could be really game changer for this multi-camera tracking problem. That's also a real scenario, application scenario, right? So you have all those cameras scattered, and in a big area, come on track people for maybe even for a long distance, a long time. That would be great. Anyway, so I'd like to get your thoughts on this. Who wants to go first?
Yeah, so okay, I'll go first this time. So
Sure.
yeah, this is certainly a great question and very interesting. And I don't know how we can get a data though. I mean, yeah, if you look at sci-fi, I mean, 20 years ago, I think those things become realistic now. And yeah, there are a lot of cameras and all that. And if there is there's drama called personal interest. So the time, at the beginning of each episode, they will show some videos that they say the U.S. has so many cameras and they are connected, and then and they can track anyone. And also in all the spy movie, you have seen that before, right? So, And some of them could be true, but the problem is that who has access to the data, right? We certainly don't. So, yeah, that would be a great question if we can have some access to that. But then again, as you know, it would be very, very difficult to have some access to the data. It's just, I don't know how, I mean, how we can do that. I mean, the only thing I can think of, Facebook recently has they collect some personal, what's the code, ORC40. I mean, they ask people around the world to wear a camera and then they have ergonomic video, so the first person view, and then they send that to people around the world and then to collect data. But that is certainly not multiple people. That's first person view, not like you put the camera on top of building and all that. But yeah, and privacy was certainly an issue, and then especially in US, I just do not know how they can allow us to use that. Okay, yeah, maybe in some lab, I mean some Java, some lab they have access to that, but for us, I cannot see that. I mean, for the next few years. So, but that's a great question.
Okay. Thank you, Hikvision.
I just want to second that. So basically, I mean, that's an ideal and purely research-wise, that's a fantastic data set. But and at least on the academic side, we don't know how to get that, and I'm afraid we will not be able to use that data set in at least in a few more years or even longer. So that actually relates to another question. So basically, I mean, we also started collecting some data set, but not for people. Okay, so then all the data set, including this workshop, we are working kind of toward a public data set. We hope that all the research community can join and can boost their research along this line. But with some type of data set of kind of related resources, so maybe they can build some data set, but just for certain industry or certain kind of facility for their usage, not necessarily for public. So.
Yeah, so I totally agree on Professor Lin and Professor Yang. And another thing I'm thinking is, can we use some, for example, adversarial image perturbation technique? So by that way, we change the picture slightly. So, but by that way, we cannot use the data for identification purpose. We can still use the data for the tracking model training. So it's a kind of synthetic data, but by that way, we can address the privacy concern, and we can have access to a larger scale data set.
Thank you. That's a very, very good idea, and it actually leads to the next question is really like whether there are ways to sort of to eliminate this privacy concern, so that we can collect data very freely, really everywhere, because somehow we have modified the images somehow. I don't really know how, but only if you guys believe there will be ways to do that, like what Hodong just mentioned. But how to do it is not clear. Or maybe there's some other wild ideas could come up later. So that there's some security folks, right? They try to encode it in a way that people cannot decode it, but still somehow the tracking method potentially should still be applicable somehow. I don't know. So I wonder along that line, I wonder if you guys, how do you guys feel about this potential? Maybe that's a direction where we could sort of somehow modify data or encode the data so that to eliminate really the privacy concern without sacrificing sort of the benefit of using data for tracking. Yeah, I just wonder if you guys share your thoughts on this. You don't have to propose a solution, but your thoughts or your confidence. So anyway, so
I think I can go first on this.
Yeah.
The reason mainly because I'm several years ago, and Jingyi and me, we actually had a joint grant, somewhat related to this one. So at that time, Jingyi has a lot of work on the camera and things. So we propose a system so that we can, once we get the data, the data we got ideally is already privacy kind of protected. And then on that data set, we can try to do some typical vision tasks, including tracking. Okay, so this one issue. So basically, if all the data we have is like this, already privacy protected, then the tracking algorithm we developed makes sense because now any data, any video is already privacy protected. Okay, so. But on the other hand, if we tune and build some tracking algorithms on this privacy protected data, and how can we guarantee that the algorithm also works on this on the original raw data? So there is some gaps there. Right? So not only for evaluation, also for tuning the tracking algorithms. So how to address this gap? I think it's open. And another issue is I think I just mentioned. So how do we so basically the definition of privacy in video data is developing, is evolving basically. So 20 years ago, we don't think the video data has kind of such privacy issue, and not, at least not that serious, because at that time, the visual recognition algorithm by itself is not reliable at all. Right? But now things change. So as I said, face recognition now is pretty much, can recognize almost everyone. But now, if you want to recognize me just by my my hairstyle, by my clothes, is still not that good, right? But what happened maybe 10 years later, you can easily recognize my identity without using my face. Okay, then the privacy, the de-identification thing becomes more complicated. So I'm not propose any answers, just my kind of my experience along this line. Okay.
Any thoughts on Min-Shan?
Well, I don't have a yeah, I don't know how to solve the issue. Because you certainly can, use some trick. Well, you can, for style gun, they can change some attribute, but the face still look realistic. So if you go that line, then you still can recognize that and recognize person, but that's for faces. Now for human tracking, if you look at holistic and you look at back view, then probably that's probably people would have a lesser concern on privacy. It reminds me back in the day when I need to collect single object data, I went on the street, but I can only record video from the back. I could never take video and just make them public. So all the other thing as you have mentioned, just have an actor to do that. But for actor, they know what they are doing, they are performing, so it's not realistic. And then the scenario that you can come out are limited, right? You cannot have many camera, you cannot have many sensor noise and all kind of stuff. So it's very limited. But yeah, hopefully we can use some gun, some and swap, and then so that people will have less concern on holistic. You cannot, you can. There was a human identification from a distance, and then, but if you just look from the back instead of from front, and for low res, maybe people would have lesser concern on this. But I don't know. Yeah.
Okay, well, thank you. Well, for the sake of time, I will stop here. And really, I'd like to thank three distinguished panelists, Hodong, Min-Shan, and Haibin. Thanks for sharing your thoughts and the ideas on this issue. Thank you. Okay. So this is the end of the panel. Thanks. Next, I think we're going to take a 5-minute break. We'll come back. Let's see, in 5 minutes. So if people's time are different, so I should not say a time here. Maybe in a, yeah, basically please come back in 5 minutes. We'll start the next session for the yeah. Okay. Yeah. Please take a 5-minute break. So come back in 5 minutes. Thank you. So Xin, are you there? Do you want to share your slide? Do you want to show your slides?
Yes, I'm here.
Okay, great. Oh, you're here. Great, great.
Yes, yes, I'm here already.
Okay, excellent. Yeah, you can please show your slides. Yeah.
Mhm.
Oh, great. It works.
Okay.
Okay,
awesome.
thank you. Yeah, yeah, we'll start in the film maybe in 4 minutes. So we just wait for people to give people a few minutes of break.
Okay, no problem.
Okay, thank you. Yeah, you can leave your slides on.
Okay.
Okay. Yeah.
Go ahead, Chan. Yeah.
Yes, we will get started. Okay. So next, Dr. Xin Wang will give a invited talk. So Dr. Xin Wang is a rising star in our field. She just graduated from UC Berkeley Cyber, and she's now a member of computer vision group at Microsoft Research. Her research interest is designing generalizable robots and sample efficient learning systems for computer vision, machine learning, and robotics. Today, she's going to give a talk about robots cross-domain of detection. Okay, Xin Wang, please get started.
Okay. Yeah. Hello, everyone. Thank the organizers for inviting me. It's a great pleasure to speak at this workshop. You may have heard many tracking work so far at the workshop. In my talk today, let's zoom in a bit to look at object detection, a key component of many tracking systems. I will share some recent work towards robust cross-domain object detection specifically. Okay, so why should we care about robustness and cross-domain model performance? One obvious reason is to ensure the reliability of our models under various conditions. We live in a dynamic world and experience constant changes all the time. For example, last year, we had an orange sky in San Francisco due to welfare. Of course, it's an extreme and rare event, but still, it poses severe challenges to our perception systems. So actually, this distribution shift issue is largely tied to the fundamental assumption in our machine learning systems. Classical machine learning theory has an important assumption that the data is IID, independently and identically distributed, which means that the training and testing data distribution should have the same statistics. So this assumption is actually very hard to fulfill sometimes. And so the common practice is to shuffle the data and do offline back training. Okay, well, Leopoldo in his keynote speech at ICML 2019 said, nature does not shuffle the data and we shouldn't. This implies that the ID assumption may ignore useful information in the natural data. And often the case, it does not apply to real world scenarios. So this systematic degeneration and the distribution shift is like a black swans which interferes the stability and generalization of our machine learning systems. Okay, we know it's an important issue here. And before we dive into the hard question of how we might remedy the issue, let's look at the major categories of distribution shifts. So first, the distribution shift, or sometimes referred as domain shift, could come from environmental changes. For example, we might see a lot of data for driving in the daytime, like this video, but at prediction time, the model may encounter various conditions like nighttime scenes, local streets, highway, and so on. So this scene level domain shift compose a large part of the natural distribution shifts. And also, this scene level domain shift can appear when the training and evaluating models, when we train and evaluate the models with different data sets, especially for evaluating the models on real world user data, which tend to be noisy and more personalized. For example, the video you see here is actually coming from my PhD advisor who installed an indoor webcam to check on his young kid. So the goal is to detect and to detect all the people and possibly track them. So you can see that the scenes and the camera angles are very different from the outdoor videos we just saw in the previous slides. Since the personalized data is usually very hard to obtain, if collecting data is not an option, we will have to rely on some like off-the-shelf pre-trained models. So here are some like prediction results from FastRCN model pre-trained on the video 100K data, a large-scale video data set. So as we can see from this video, not everyone in the video can be detected all the time. And for example, the woman on the sofa was never detected. And there are so many wrong predictions, like predicting a truck in front, truck in the picture in many of the frames. And this distribution shift has caused significant performance drops in real-world data. And aside from the scene-level domain shift, the model may also encounter new concepts and rare events. For example, a plastic bag suddenly appears in front of this Formula One racing car. Hypothetically, if we installed a self-driving car like a system on this car, how would the perception system to handle it if it never sees such example during training? It's very critical because it's related to the safety of the drivers. So such semantic level domain shift is another big challenge to build a reliable perception system. Okay, we talk about like a scene level and semantic level domain shift. And as a note, there are also adversarial examples that can lead to the distribution shift. In this talk, I will mainly focus on the natural shifts at prediction time, such as the scene level and the semantic level shift. Okay, so let's zoom out a bit to look at the big picture. To build a robust cross-domain object detector, we need the model to handle the changing environments, aka scene level domain shift, and also semantic domain level domain shift, like dealing with new concept at prediction time, etc. So in the literature, there are settings like domain adaptation, auto-domain generalization, single domain generalization, etc., to mainly deal with the contextual changes. And also there are few-shot learning, class incremental learning, lifelong learning, etc., to deal with semantic changes to handle emerging new concept at test time. So in my talk today, I will share some of our recent work using self-supervised learning to build robust object detectors. And I will also talk about providing new online continual learning setting and benchmark to handle both the environmental changes as well as new tasks continuously. So, okay, I mentioned self-supervised learning. Self-supervised learning is no longer an unfamiliar term for many audience. For those who are new to the field, in self-supervised learning, the system learns to predict one part of its input from other parts of the input. In other words, a portion of the input is used as a supervision signal to a predictor fed with the remaining portion of the input. So the deep learning guru Ian LeCun said, okay, self-supervised learning is like the cake of the intelligence. Supervised learning is like the icing, and the pure reinforced learning is like a cherry on top. It's a really important problem to study in the field. And in our context, the one question we can ask here is, can we discover useful signals from our training data itself to improve the model robustness? So actually, a research work from Diane Hendricks et al. Shows that using self-supervised learning can improve the model robustness and uncertainty. So the original work is done on the image classification task, and the authors find that the training an image classifier with a simple self-supervised task, rotation, basically predicting the rotation angle of the input, can improve the out-of-distribution classification accuracy. This finding is very inspiring, and one may ask, is that really generalizable to more situations or more tasks? If self-supervised learning will still be useful for more complex tasks like object detection and tracking. So this is like, before we answer that question, let's take a step back to look at the commonly used self-supervised tasks. So they are often on the image level or pixel level. For example, predicting the rotation angles, or in the jigsaw task, the model needs to characterize the permutation order of the image patches. And in colorization and image reconstruction task, the model needs to predict the color from the grayscale image or predict the pixel values of the missing patches. So these tasks often help the model to learn a global representations of the entire frame, entire image, which might be helpful for the model to understand the semantics of the input. However, in object detection, we need to answer two questions. What is the object and where is the object? In this situation, we will also need instance level or local representations to help our models characterize and localize the objects in the scene. In the literature, instance level self-supervised learning is a bit underexplored, and I will talk about some approaches along this line for object detection. So to begin with, I will talk about robust object detection via instance level temporal cycle computing, which leverages this instance level self-supervision to improve the auto-domain generalization of object detection. So this work was presented as ICCV this week, and it's a joint work with folks from Berkeley, ETH, and the UCSD. So in this work, we focus on auto-domain generalization. That is, an object detector is trained on one domain, say daytime images, and then we tested the other domains like raining or nighttime images. So here the model doesn't have any prior information or access to the test domain data during training. So the setting is relatively strict among the related works. For example, in this figure, we illustrate the related settings in the literature. First, domain adaptation. So it assumes the model can access some amount of target data, usually unlabeled during training. And then we test the model performance on the target domain. So previous work often used feature alignment-based approaches to learn domain environment features. And second one, domain generalization. It often aims to learn generalizable representations from the diverse training domains and then test the model in an unseen domain. And the third one, auto-domain generalization or single domain generalization in some literature is the one we consider in this work. It assumes that the model only sees one training domain and should generalize to many test data. So to enable such OOD generalization or out-of-domain generalization, one way is to augment the in-domain data with OOD samples so that the model can learn domain environment features. So in this work, we take advantage of the spatial and temporal information in videos and use the negative matchings in the neighboring frames as the OOD samples for the in-domain objects. So you can see that, like, instead of matching the most similar objects, the matches are turned to be those in the far distance, so like which is not very similar to the original object in orange. We will talk about it in more details. So the intuition is that the negative matches may serve as the out-domain instances or near boundary instances. Joint learning from the in-domain samples together with the near boundary samples can often lead to more robust features. So to realize this idea, we propose an instance-level temporal cycle computing task, a self-supervised task operating on the region features in the videos, which is usually used as an auxiliary task when training the object detectors. So here we use phosphorus in our base object detection architecture. So how does it work? The first step is the forward matching from timestamp T0 to T1 in order to find the matching candidates. So namely, we name the like matching candidates as soft targets. So the soft target, the term soft target means that instead of using the feature from like one proposal in one particular proposal, we will find the aggregated target among all the proposals for stability. So, okay, for a pair of frames in the video, the cycle computing task operates on the instances features produced by the base object detector, the region proposal network. And for object UU in T0, so it will need to find a soft target in T1. So suppose there are N1 candidates in candidates in T1, we first calculate the L2 distance between the reference object U and other candidates V in T1. And the soft target is defined as the weighted average of the candidate features. So more distant the candidate is, larger the weight is. So the soft targets, again, will serve as the auto domain samples to the in-domain instances. So similarly, the backward pass requires the soft target at T1 to match the original object at T0. So we view this backward matching as a classification task, where recursive entropy loss is adopted as a training objective. So basically, we will again use the similarity scores that measures distance between the soft targets in T1 to all proposals like in T0. And so loss is the course entropy loss with the ground truth as the original reference object. So you may feel confused about the commonly used term like a cycle consistency. So the major difference between the two is that cycle consistency often matches the most similar patches in the JSON frames. So in this case, cycle consistency may have a trivial shortcut solution to only match the closely located objects, ignoring other information like texture or shape. To remind you that the goal here is to improve the robustness of object detection, which turned to, instead of tracking, we wanted to make sure the model is generalizable among the instances within the same class. So that's the major difference. So we named the test task cycle confusion since the matching process will mix up the instance features. Similar to maximum entropy regularization, this task will encourage the model to explore latent structures shared among the in-domain instances and the soft targets on the boundary. So here's another figure to show the matching entropy values. So this is the forward matching probabilities of the instance features. And each row refers to one object in T0, and each column refers to one object in T1. As we can see, compared to cycle consistency, the matching probability distribution of cycle confusion on the right is flatter with higher entropy values. And you can see that on the left, the cycle consistent one tend to matching the identical objects across the frames. We will show more results like this later. And the overall framework is shown here, where the self-supervised task share the same backbone and region proposal network with the detector, and both the detection head and the self-supervised head are jointly trained. So at inference time, we can remove the self-supervised branch and use the original object detection for inference, detector for inference. Okay, so for evaluation, we consider large-scale driving video datasets, B200K, and Waymo open data, and consider distribution shifts like a different time of day, weather, and camera angles, etc. So here again, like we train a model on one domain, for example, daytime, daytime images on B200K, and then it will directly evaluate on other domains like nighttime scenes or other data sets like Waymo, cityscape, etc. Okay, so here are some results. So this bar chart presents the results when the model is trained on the front left camera in the Waymo data, and then directly tested on the B200K nighttime scenes. So as we can see from the figure, so the baseline fast scene model, which is denoted on the as the white bars on the left, obtains about like a 19.62 points of AP, and our approach on the in the light blue bars on the right achieves like about like a 26 points in AP with like over 6-point improvements, and also it outperforms other self-supervised tasks like rotation, jigsaw, and cycle consistency tasks. So to mention that, it's actually rotation task is actually pretty effective here as well. It's on par with the cycle consistency task, which leverages the spatial and temporal information in the video as well. And the image, like a rotation task and the jigsaw, will only operate on the image level information. And similar results can be observed in their domain shift by time of day. So here, this is a bar chart for training the model in B200K daytime, and directly evaluates the model on nighttime scenes. So, and this, you can find more result in the paper, but in this particular figure, we show like sometimes the cycle consistency task may perform worse compared to rotation task. The more quantitative evaluation can be found in the paper. Okay, so aside from the quantitative evaluation, we show some matching candidates in both cycle consistency and cycle confusion tasks. On the left, we can see that the cycle consistency task turned to match the closely located object, which usually the object is itself. And in cycle confusion, by this design, it will never matches the closely located object, but rather it will prefer the distance objects or like negative matches, so that it can improve the generalization a bit. And here are more evaluations. Again, on the left side is what we get from cycle consistency, and on the right is the cycle confusion task. Okay, that's the auto domain generalization. We also noticed that this jointly training framework, despite its simplicity, can also improve the unsupervised domain adaptation when the test domain data is available during training. So the extension is actually pretty simple. You can just run your self-supervised head on the unlabeled test domain data during training. So we find that this approach, despite this simplicity, is actually outperforming many complicated methods on cityscapes. Here we didn't use cycle confusion since it needs a video to operate, and we use the simple rotation task here. We find that it's already outperforming many previous feature alignment based method with a faster training and evaluation. So in this sense, we make conjecture using self-supervision as a regularization might be a unified solution to deal with various condition, various distribution shift settings. So more study could be done in this direction. And before we go, there's finally I wanted to show them real demos on what it looks like in some bounding box visualizations. For example, the model is trained on the daytime images and tested on the challenging rainy nighttime scene. So you can see that despite the model have never seen some challenging cases in nighttime time, they can reasonably predict the bounding boxes. So the model and the code are paper are online. So if you're interested, you can check them out. So in this related line of instance level subsupervised learning for object detection, so there are two recent works which shows that this using region priors can help the model transfer to new concept with reduced amount of data and the labels. So for example, data rag unsupervised pre-training with region pairs for object detection, we use selective search to provide region pairs to help the model learn useful representations, and the region similarity representation learning to learn some instance level similarity scores for a better backbone. So you can also check the details in those papers. So, okay, now let's take one step further from auto domain generalization. In the previous work, we assumed the test domain test domains are static, and we don't consider whether the changes within the same domains. So the situation becomes like more complex as we explore non-stationary data at test time and adapt the model to continuously changing environments in an online manner. So for example, an embodied agent may observe new objects as it moves around, and the things keep changing along the agent's trajectory. Learning from a stream of data online allows the model to directly learn from non-ID data and doesn't break the natural distribution of the data. So in the typical static offline setting, so we can shuffle the training data and repeatedly train the model on the same training data for a lot of epochs. And after the model is trained, we will evaluate the model performance on a head of test set, which may or may not have the same distribution as the training data. So this setup actually breaks the natural structure of the data. As Leopoldo said, nature does not shuffle the data and we shouldn't. Again, we know it. So what might be a more realistic settings here? So actually, let's use our embodied agent example again. So when an agent starts to explore, they may not know the category of interest beforehand. And when a new object comes in, the model needs to learn new objects with the newly observed samples. So they cannot collect offline data to do batch training for a long time, but to learn from the few samples in an online manner. And usually this learning should happen in almost real time. And as the agent keeps exploring the environment, the context may change and the view angles will change, blah, blah, blah. And since the learning process happens almost instantly, we will also need to know the model performance periodically along the time. So therefore, both the training and the evaluation should be performed in the video stream, same video stream in an online manner, similar as how a reinforcement learning agent might learn. And in this exploring process, the number of classes grows gradually as the agent moves around, and the emergence of the new task should follow the trajectory of the agents. So also the frequencies of the object instances may vary from task to task following the natural distribution. So so this is the setting I just described is like the online continuous setting. To study this setting, we will need like a long range video streams that can capture continuous changes in the scene. And also the emergence of tasks should follow the natural pattern. So in the previous like a continual learning literature, people often manually split tasks in a sequence when all tasks may not be seen at all during training. In reality, people may revisit the same place and the old task may occur like after a long time. So the third one is the learning process should happen in an online manner without repeatedly learning from the offline data. So together with like folks from like a Carnegie Mellon University, we introduced a new ego-centric datasets with over 100 videos named Objects Around Krishna, or OAK for short, at this year's ICCV as well. So what's unique about this dataset is that they were collected by a single person, Krishna, a former computer vision grad student spanning a 9-month lifetime. So this ensures us to have a consistent long video streams recording the lab pattern of real person. So in these videos, there are frequently visited places like home and the university, and occasionally the students travel to other places, and you can see the diversity of the from the geolocation maps. And with this unique source of data, we further provide the bounding box annotations for over 100 categories at a frame rate of 0.5 FPS. So the resulting data has over 300,000 bounding boxes, and it currently covers 16 hours labeled videos, which is like a subset of the raw videos. Here are some like a visualization of the data set. So what you see here is like the green box will be used to denote the same categories, and the red box denotes the new categories when the student enter a new thing. So here's another video captured in the summertime. You can see that these videos are captured through Google Glasses, a type of like a height-mounted camera. So you can see like motion blurs in many frames and the more object occlusions compared to third-person view videos. It's relatively challenging compared to the existing detection data sets. Okay, so actually, there's several challenges in this data set. First, it provides a natural long tail distribution in the object categories. For example, there might be a lot of people in the scene, but only one manhole in the picture. And also, the objects from the same categories may appear after a long time, thus easily cause catastrophic forgetting. And also, the data set may have a significant domain shift. So for the training and the evaluation setting, so what we do is like to extract the one frame every 10 seconds from the video stream to form a hideout test set. And then the model is fed with the stream of training samples online, and then we evaluate the model every k time steps on the hideout test sets. And we also consider two setups, whether the categories of interest are known beforehand. So in the known vocabulary settings, the model is provided with a fixed set of categories, although the data of those categories are coming in a streaming order. And in the unknown class vocabulary setting, the model needs to predict IDK or I don't know when a new task appears for the first time. So the learned categories should increase gradually as more tasks comes in. So the second unknown class vocabulary setting is more challenging and more realistic. So we benchmark both in our work. So we also introduced a set of like evaluation metrics to evaluate the model overall performance on the entire video and the transferability and forgetting in the learning process. For the sake of time, I will not go into too much details here, and you can check on the paper or I can discuss offline if you're interested. So I would like to show like some like a quantitative evaluation results on the known class vocabularies first. So here we like adopted the commonly used continual learning methods, incremental fine-tuning, EWC, ICAL to object detection. So those methods were originally designed for image classification. So in this figure, the pink bars are the performance on all categories, and the orange bars are on the top 20 common categories. And we also provide the results to evaluate forgetting. And here the red bars are the 20 rare object categories. So we can see that overall, the online learning performance of the existing methods only achieves about like roughly half of the offline training performance. So among the continual learning algorithms, ICAL, which uses external memory, achieves the best external memory to store samples for replay, has the best performance compared to other methods like like EWC and incremental fine tuning. But using like a external memory for replay may not be able to achieve like a real-time learning online. So better methods that can learn and adapt quickly are actually needed here as well. So also for forgetting, there's actually like a lot of forgetting compared to the previous like method. So I call again has a better performance, but there's still pretty much a gap from the rare objects, which is the bottom like 20 objects. You can see the forgetting is usually happen for those like rare events. So if we also need like a methods that can effectively deal with the rare events, the forgetting of the rare events. So we hope that this realistic problem setup and the benchmark can foster like future study towards human-like models in continuously changing environments. So we set up a website on SEP to release the data and the evaluation tools. So you can simply download the data, train the model, and submit your result to our evaluation set for testing. So you can definitely check them out if you're interested. Okay, so going forward, in my humble opinions, there are a few like exciting problems along this line. For example, a big question is, what is the general framework to address the distribution shift? In this talk, I mentioned that like self-supervised learning seems to be promising to improve the robustness of object detectors. And more study like whether it's just like a big model, so you can always use like more data, use self-supervised learning to train the model. Would that like improve the robustness? And also, does this work for more downstream tasks such as like object tracking, segmentation, etc.? So I personally feel like we need a general framework which can systematically address those like distribution shifts. And also, we need approaches to address the catastrophic forgetting issue in continuous learning. So questions like what might be the useful inductive biases one can use? And should we do something like a test time adaptation to address the issue? Personally, I feel like those are the open questions. And also, moreover, we need more efficient methods for fast online learning. We cannot just collect offline data all the time to repeatedly learn. We wanted to find what is the efficient learning paradigm so that the model can quickly grasp a new concept in almost real time. And hopefully this will be very helpful for the audience, and I'm happy to take questions. And yeah, that's all for my talk today. And feel free to contact me if you have like more questions. Yeah, thank you.
Yeah, thank you. Yeah, if you have any question, please directly ask or just comment in the chat window.
Hello, I will ask a question. So thanks for the nice talk. The adaptation, that direction is very interesting. Because during the panel we talked about like whether we can adapt from synthetic data to real data. I was wondering if you can comment on that, see whether the techniques you're proposing or the techniques you will be investigating could potentially be applicable or be effective for this problem of adapting from synthetic data to real data in the detection or tracking that kind of task.
Yeah, that's a great question. I mean, ultimately, we wanted to achieve this, like we have a lot of synthetic data out there, and we wanted to close the gap between the synthetic data as well as the real world data. And there's actually one like a project, like my colleague and I are actually pursuing is actually finding like whether the synthetic data could be used as a useful data augmentation for the real world data. For example, we have now some people may find like a copy pasting. You can use like a copy pasting objects on the images to help the generalization. And what if you have a bunch of like a synthetic images? You can control the lighting, like shapes and diversity of the objects. Those like things might be very useful as a tool of like a data augmentation to combine together with the real world images. So like that's a particular one example how we can maybe able to use the tool to improve the transferability and or adaptivity between the two. So yeah, I think definitely there's a lot of possibilities there and definitely needs like more study in this line.
Thank you.
Yeah, thank you.
Any more questions? Okay, if no more questions, actually, I will ask a question. I think similar to that line for also domain problem, I think the data is really an important aspect. I think for example, if you can just for some use some approach to get those data for those also domain things, right? This will make the problem much easier. So do you have any comment on this aspect in addition to the modeling? What's the technique we want to invest in data to resolve the domain problems?
Okay, so to make sure I understand the question, is that about like are you suggesting what are the techniques to handle out of domain generalization from the data perspective?
Yeah. So this is my question. I think you mostly talk about from the model perspective, but that perspective, the data perspective.
Yeah, that's a great question. I definitely see there's a like a different line of work in this term. So basically, one way to improve like a generalization, definitely you can collect more data. You try to make your data sets like more effective. And actually some other recent work like a clip models or like which shows like a pretty good like a zero-shot generalization. If you look at the method, it's actually the method itself might be like a relatively straightforward, but it's actually have very good performance. So this indicates that the data is actually pretty important in this situation. So definitely like collecting more diverse information is very helpful, but you cannot exhaustively like collect all the data. So one thing I found particularly useful might be the test time like adaptation. So basically, when you make a prediction, you already access your test domain data, which is at least you have a single image you can use. So if you can mine some, discover some like useful information from your test example and use that to adjust your model or to try to augment your model, so those might be more helpful in a sense to solve this like auto domain generalization. Although this is more like a hypothesis from my personal perspective. So so to summarize, it's more like you can collect like more data to learn like a generalizable representations. And on the other hand, like discovering like a useful information from the test data is another way to address the out-of-domain generalization problem.
Thank you.
Yeah.
Okay, if there's no more questions, probably can conclude the talk from Xinwang. Yeah, thank you very much for your great talk.
Okay, thank you everyone.
Okay, thanks. Yeah, so next we'll have the talks from the winner. Yeah. Chandru or Satya, do you want to introduce the winner talk?
Okay, sure. Yeah, thank you. Okay, so next one we'll have the first track, which is a top-down view track. Winners talk about their methods. So the first talk is from the rank #1 from the Alibaba group. So they're titled from a camera view checklist to top-down view trajectory, information aggregation at different levels. So probably Fei Du from Alibaba. Hello, Fei, are you there? Can you share your screen maybe now?
Yes.
Okay, we can see our slides now. Maybe you can start. Thank you.
Okay. Hi, everyone. I'm going to show our method and results here at the MMP Tracking Challenge Workshop. We are from Dharma Academy Alibaba Group. I'm Fei Du. The title of my talk is From Camera View Checklist to Top-Down View Trajectories, Information Aggregation at Different Levels. First, let's have an overview of the challenge. There are two subtracks, tracking from top-down view and tracking camera view. We need to track the target in each camera view and get the trajectory of every person in top-down view. The whole task is challenging due to factors such as collision and multi-camera views. Our whole pipeline includes target association in camera view, information aggregation in top-down view, and target matching in camera view, finally. Let's first take a look at the camera view tracking pipeline. The pipeline is simple. A detection model is first applied to detect the target in each camera view. Then we extract features for all detection boxes and use deep sort to associate them. Finally, we use post association to associate broken tracklets and post interpolation to interpolate missing boxes. Here we use the open source UIUC as our best detection model and train on the train and validation sets. We find that the generation ability of our model on the test set is really not good. And we have verified from the organizer that the test set can be used to do training. So we have another model that is fine-tuned on the test set. And I will introduce how we fine-tune the detection model later. For training model, we use deep sort to associate detection boxes. The deep sort uses common filter to predict the targets and a cascade matching strategy to associate them. It matches the tracklets with detections by first using appearance similarity and then using IOU of the bounding boxes. Here we use a fair MT implementation. And for the appearance model, we use the open source strong baseline for deep person re-identification. It uses several tricks and builds strong baseline. We fine-tune the pre-trained model on the train and validation sets. Since the targeting different frames may not be associated due to occlusion or appearance change, we use post association to link broken tracklets. It can be viewed as tracklet level matching compared to box level matching in deep sort. This is also our first level information aggregation. This strategy has been used in our solution for the ECCV Tau challenge. And the change here is that we use a clustering method to separate the tracklets to different groups based on their appearance similarities. Then we link the tracklets in the same group to one tracklet. The appearance for each tracklet is calculated by averaging all the target appearances in this tracklet. Since the target may not be detected or associated in every frame, we also use a post-interpolation strategy to interpolate missing bounding boxes in each tracklet. We restrict the interpolation interval to maximum 50 frames to avoid high false positive. Next, let's take a look at how to aggregate information from camera view tracklets to generate top-down view trajectories. We get together all tracklets in one scenario from different camera views and use the hierarchical clustering method to separate the tracklets corresponding to the same target to the same group. The clustering is only based on their appearance similarities. Then we solve the 3D coordinates for each target in every frame. Post-processing is finally used to purify the trajectories. Here shows our detailed strategies of tracklet clustering. And this is our second level information aggregation. We first cluster the tracklets by using the cosine distance in hierarchical clustering algorithm. The appearance for each tracklet is also their mean features. Then we select the center point of the bounding box as the key point to solve the world coordinates frame by frame. We have also tried the head point and the foot point, but the center point is better. As we can see, we can draw a half line from each camera to the center point of the target. Ideally, the half line from different cameras should intersect at one point. However, since the detection may not be accurate, the half lines may not intersect. So we solve the world coordinates by calculating the middle point of the common perpendicular of every two half lines. Note that we can solve one 3D point with half lines from every two cameras. We get the final world coordinates for each target by calculating the mean value of all the solved 3D points. We use three tricks here. First, if there exists wrong association, the bounding boxes in one tracklet may not belong to the same target. Directly calculating their mean features may not be a good choice. So we cluster bounding boxes in each tracklet to two groups and select the large group to calculate the mean features to represent the tracklet. Second, since there exists wrong association, when solving the world coordinates for one target, not all bounding boxes represent the same target. For example, here the target in camera 2 is not the same as the target in camera 1 and camera 3. In that situation, the common perpendicular between like camera 2 and camera 1 will be very none. So we drop the 3D point whose corresponding common perpendicular is larger than 400 pixels. Finally, this is our third trick. Some 3D points may be far away from others. Directly and averaging them need to poor accurate. So accuracy. So we drop some outliers by clustering the solved 3D points for each target to two groups and select the large group to calculate the final mean coordinates. Our third level information aggregation is the post-processing. Since we have multiple cameras and we can get one trajectory with only two cameras, there may exist duplicate trajectories. Here, we introduce the track AMS and the track merging strategies. The track AMS is similar to the box AMS. It is used to drop short trajectories who are overlapped with other non-trajectories. If the average Euclidean distance between two trajectories is less than 30 pixels, we think they are overlapped. Here, another metric means IOS is used to determine whether to remove or merge tracklets. IOS means the frame intersection over short trajectories between two trajectories. If two trajectories are overlapped and their IOS is larger than 0.5, we remove the short trajectory. If their IOS is less than 0.5, we merge them. Finally, we also perform track interpolation to interpolate missing targets. And let's see some ablation study here on the validation set. From the first table, we can see that the post-association can significantly improve the IDF1 score, and the post-interpolation may improve the motor score since we fill up the missing bounding boxes. The second table shows that the results of the shows the results of the top-down view tracking. We can see that the post-processing strategy in camera view tracking can help improve the performance in top-down view tracking. And all the post-processing in top-down view tracking further improve the performance. We get a high top-down view tracking performance here, but our camera view tracking is a little worse here. So we construct another pipeline to improve the camera tracking using the top-down view tracking results. We first map the 3D points back to each camera, and then perform appearance-based matching and Euclidean distance-based matching to match detection bounding boxes to the tracklet mapped from the top-down view. If there is no detection matched, we interpolate a new box. Compared with the directly tracking in camera view, our top-down view to camera view match strategy significantly improves the performance here in both multi and IDF1 scores. As I mentioned before, we also fine-tune our detection model on the testing set, since the generalization abilities look good. We use the top-down view to camera view matching results to select high-quality pseudo labels and fine-tune the detection model for 20 epochs. The experiments on the test set shows the fine-tuned model improves the top-down view tracking results by about 0.5. It also improves the camera view tracking performance, but we focus the top-down view tracking here. And we then do a model ensemble. We first concatenate the camera view results from two detection models and perform information aggregation in top-down view. Tracklets corresponding to the same target will be clustered to the same group, and the corresponding top-down view trajectories will be can be solved. The ensemble model improves the Morton score by 1.0, and finally we got a 96.4 Morton score on the top-down view tracking. Here are the leaderboards. We achieve the best results on Morton and IDF4 metrics in top-down view evaluation. We also get the best IDF1 score in camera view evaluation. And this is attributed to our camera view to top-down view matching. Our code is released. Welcome to clone our repository and have a try. Thank you.
Okay, thank you. Yeah, thank you for the talk. So we still have several minutes. Anyone have any questions? Okay, so now I have a question indeed. In your slides, I think you mentioned that when solving the 3D coordinate, you need to merge. Yeah, the next slide, And in this slide, you need to merge and you need to cluster those 3D points called merge and use the mean, right?
Yeah.
In the third trick. But I saw that in the second trick, you already merged do a triangulation from all different cameras. You already merged those 3D points, right?
Yeah.
But
we merge the tracklets.
Oh, you merge the tracklets.
Yeah.
So these 3D points are still from each camera, right? In the third trick.
3D point is solved using the results from two cameras. Every two cameras can solve 1 point.
Oh, I see. You do a pairwise triangulation.
Yeah.
Okay, thank you.
Yeah, thank you.
I have a question. For the ReID model, how effective is that? Did you fine-tune the ReID model on this data at all, or you just directly use the pre-trained model without any adaptation?
We fine-tune the appearance model on the train and validation set. Yeah, we select some. Yeah, we sample some data and fine-tune it.
Okay. Do you see the how much does it improve after fine tuning? Do you have a sense?
If we don't fine tune on the this set, this computation data, I think maybe we will the performance will drop by about 10 to 20 points.
I see. Oh, so it's pretty important.
Yeah, it's pretty important.
Okay, thank you.
Okay, thank you. Thank you again, Yafei, for the great presentation.
Okay, thank you.
Yeah. So next, maybe we can have a second winner from University of Science and Technology of China, Si Zewu.
Yeah, yes, I'm online.
Okay. Yeah, can you share your screen? Thank you.
Yes, but I'm the third one. Yes, I'm the third place. Maybe there's something wrong with your ranking, or the second place just didn't report their results.
Yeah,
I'm the third one.
Talk about it in the camera view. Sorry, in the camera view track.
Oh, okay, that's okay. That's okay.
So you are the second talker, speaker in this track. Yeah.
Okay. So here, can you see my screen?
Yeah, I can see your screen now. Yeah, you can start.
Okay, let's start. Hi everyone. I'm pleased to present my solution to this multi-view tracking challenge. I'm Si Zewu. I'm undergraduate in University of Science and Technology of China. My solution here is an online solution, and it's quite a traditional one. It's detecting and associating the 2D results and get the tracking results. So you can see from the multi-view images, we got the detection, so got the human detections, and then predict the human poses and extract the real ID features. So we use all of these attributes to update the trackness, the set of trackness which is initialized by an empty set. So here we start by some definitions and the requisites of our approach. We need synchronized multi-view cameras and their parameters. And here I'm going to define a tracknet. A tracknet is a tracked person, and its attributes include a person ID, and its status is include new if we build a new one, or it's tracked, or it's lost. And here we also have 3D poses. It's reconstructed from the multi-view 2D poses, and we also have the real ID features in every camera view. And the operations on the trackness include building a new one, and add this new tracknet to the tracknet set, and also we can update the attributes of a tracknet when we have detections from a new time frame. And here we also need to define some associations. The first is 2D to 2D association. So we need to associate 2D results from every camera view. The affinity on 2D poses are calculated by exponential minus lambda pose and dpose. Lambda pose is a constant, and the dpose is calculated by the minimum distance between 3D arrays. So that's showed in this in the picture on the right. So it's a minimum distance between 3D arrays, and the affinity on real ID features is the inner product of normalized real ID features. So the final affinity was computed by a weighted sum by these two affinity value. And 2D to 3D association. We need to associate the 2D detection results to the trackness on the 3D space. So this time the distance of pulse is the 3D point to this 3D ray, which is the line perpendicular to the point and the ray. And also the ray ID features is still the product of normalized ray ID features. And also the final affinity with the weighted sum of these two values. And also we have 3D to 3D association. That is when we reconstruct the 3D human poses from multi-camera views. We need to associate the reconstructed person instance to the trackness in the tracknet set. And so this time the distance is the distance between two 3D points, and the affinity on ray ID features is still the inner product of normalized ray ID features, and the final affinity is still the same. So here we have two methods. The first is reconstructing and associating. We can reconstruct the 3D human person. We can reconstruct the 3D human poses, and then we decide if this is a new one. If this is new, we add it to the set of trackness. If this is not, if this was matched, if this is matched to one of the tracknet in the set, so we update the tracknet, and this approach achieves 85 on MOTA and 91 on IDF1. So this is not a very good result. And also we have the second method, associating and updating. So when we get started, when we initialize the trackness, we also need to reconstruct the human person in the first frame. And then when in the coming frames, we just need to do 2D to 3D association. So when the 2D results is matched to a tracknet, we can update the tracknet. And if this is not matched to any tracknet, we can still forward it to the 2D to 2D association, and we can reconstruct a new one. So we can add a new. So when somebody opts in, we can add it to the set of tracknets, and this method will achieve higher scores on both of the metrics. I think that's because the 2D to 2D reconstruction is not that robust. So when we got a false reconstruction result, the tracking performance will be influenced further. So here I want to explain some more about the second method. That is, so when we look at this, when we look at the 2D to 3D matching and 2D to 2D matching, that's easy to understand. When 2D results are matched to tracknet, we just update it, and now I need to explain why I will forward the unmatched ones to reconstruct new persons. That's because maybe somebody will walk in. So if we don't do this step, we will lost many tracknets. And also we need to inquire whether the reconstructed one is a new person or not. So false negative 2D to 3D matching results will need to ID switch. So this step is very necessary to avoid such ID switches. So this query is inherently a 3D to 3D match. We match the reconstructed human instance to the existing TrackNet. So if they are matched, we just update the matched TrackNet. If none of the TrackNets are matched to the reconstructed one, we can add it to the set of TrackNets. Here I want to add some details of our method. That is, when we get the 3D poses, how we map it to the map locations. Here I use a weight sum of the first two dimensions of the pose coordinates. So the weights are nulled from the training dataset by gradient descent. And about the models, the detector is a faster RCNN trained on COCO dataset with the detection toolbox. And the pose estimator is a HRNet trained on COCO dataset, again used on pose. The reality model is a Resident 50 trained on market dataset, and here is the link to the Strong Base 9 project. Any questions?
Yeah, anyone has any questions?
So what kind of tracking method you use? I think you just mentioned the affinity matrix, but not mentioned the tracking method.
You mean the way to
like how you associate the detected bounding box with previous trajectory?
So that's in the 2D to 3D part.
Okay.
So when we got 2D detections from multi-image views, multi-view images, we will calculate affinity matrix from the detected results, 2D results, to the existing trajectories. So it's in this step.
Okay, I see. Thanks.
Okay, hi, Susan. I also have a question. When you generate the top-down view results, I think you have slides talk about you have a weighted, yeah, this one. So this X map is the final XY coordinates of the tracked person in the top-down view, right?
Right. Yes.
So K here is just a number of camera, right?
Number of camera. I think in this place there's the pose is a 3D pose. So
yeah, pose is 3D pose, but here you just want to learn. So I'm not quite sure how you generate it, because eventually when we evaluate top-down view, we need.
Oh, you mean how I generate the training data in the
no, how do you generate the final results? For example, in the top-down view, we need to know the X and Y coordinates when you generate the tracking results, right?
Yes, in the in the process of tracking and association, at first, a 3D human pose was reconstructed from 2D results after the 2D to 2D association, and this 3D human pose is updated each time after the 2D to 3D association. So finally, we have 3D poses in each time frame. So after the tracking process, we got 3D poses, and from the coordinates of the 3D human key points, we use the first 2 dimensions as x and y, and we take a weighted average to
I see. Okay.
To calculate the map location.
Okay, thank you. Yeah, that answers my question. Yeah. Okay, so if there are no more questions, let's go to the next. Thanks again, yeah, for a great presentation.
Thank you. Thank you.
Thank you. So next one, let's go to Fujitsu Research, Fan Yang.
Yes, I'm here.
Okay.
Can I share my slides?
Yeah, sure. Go ahead. Okay. So maybe you need to stop your sharing.
Okay.
Yeah. Okay, thank you. Okay, Fan, you can start. Yeah, we can see our slides. You can.
Thanks very much. Hello, everyone. My name is Fan Yang from Fujitsu Research. First, I would like to thank the organizers invited us to have a talk here. And then I'll try to introduce our solutions for this challenge, which is head-based multi-camera, multiple people 3D tracking. Our proposal is like this picture shows. We'll try to use the head, which obtained each camera view to generate the 3D track lists. And then after get the head track lists, we project it to the ground plane so that we can get the top-down view track lists. The motivation to utilizing the head tracking is based on 3 reasons. First is naturally cameras are mounted in a high location, and thus the head could be visible for most of the cameras. Second is challenge to obtain the complete body bounding boxes in plenty of application tasks. Third is multi-person head detection is much faster than utilize the multi-person pose estimation. Using head information can accelerate the speed of the whole system. How we get the head detection? Since there's no bounding box of the head in the training data, we utilize the crowd human dataset and the COCO dataset to train a bounding box detector. Then we estimate the head detect bounding boxes in the challenge test set. After we get the head bounding boxes, we try to associate them across views. We need at least 2 camera views to obtain the 3D head positions. This is for a single person's case. We need to find the correspondence of the same head in different views. In the challenge, since we have multiple persons, it became more challenging as we need to distinguish different persons across the camera views. To address this problem, we'll first propose our offline tracking framework. We utilize all the camera bounding boxes in each camera view and perform single view mode trackings to generate the track lists within each camera view. Then we perform a temporal interpretation to infuse the missing bounding boxes. After that, we'll calculate the cross-view epipolar geometry distance between each checklist, and then based on distance, we associate them together. In the end, we'll calculate the 3D trajectories by the triangulation and perform another interpretation to get the 3D checklist results. Meanwhile, we also propose an online tracking framework. The basic ideas, we try to slide in the whole videos into multiple sliding windows. Within each sliding window, we'll perform exactly what we did for the offline check-ins. Then we try to calculate the overlapping path distance of each sliding window, and then link them together to get the final results. For some details, single view check-ins, we just performed the basic mod algorithms. We only use the IOUs for the tracking without the appearance. Then after we get the bounding boxes, we try to calculate the epipolar geometry distance. For 2 camera views, from the head bounding box center, we can project the epipolar line to another view. Therefore, we can calculate the cross view distance for each of them. For the single frame case, for example, if I have 2 cameras and 2 persons, we may get a matrix which has the epipolar distance, and we'll select the minimum one for the assignment. We're setting a threshold to approach this. Since a single view may not robust, and in our case, we already have a single view checklist. Therefore, we perform multi-frame jointly calculate the epipolar distance. The matrix became like a tensor, multiple values available. Then we're considering all the values together when we do the associations. It might look like this. If we only have a single view, maybe the association relationship is very limited. And then after we increase the frames, we get more robust relationships. In our test, we found if we perform the multi-frame association, then some association errors can be avoided. For example, like this person's here, if we only perform single view association, then the ID could be assigned to different one. However, if we try to utilize multi-frame together, then the ID could be correct. After we obtained the cross-view checklist relationships, we just perform this 3D triangulations and get the 3D trajectory for the head. Then we project the head location to the ground plane to obtain the final results. Meanwhile, we perform the temporal interpretations. This is for the single view interpretation. We just use the front and after 2D bounding box to infuse the missing ones. For the 3D ones, we just perform the 3D interpretation and get a missing 3D location. In our online approach, since we have multiple windows, we calculate the overlapping part, the Euclidean distance, and then to associate them together. In our offline framework, we can approach a model value of 0.91. Offline is a little low, 0.78. After we merge them together, we can get 0.92. And if we can do our interpretation and smoothing the checklist further, we reach a final score. Here, compared to other winners, our IDF1 is relatively low. One main reason could be we do not utilize the appearance feature, and in many frames, the head are invisible. There are some illustrations for our result. Here, we analyze 2 limitations for our method. One is current head detection performance is unsatisfactory because we did not train our head detections and training data. We can find a lot of false negative and false positives in the following pictures. And this will impact the final tracking results. Another is for some views, especially for the head, we only have one camera view detect the head bounding boxes. So for such common problem, we suppose if we try to relocate the cameras, for example, and within the 3D bounding boxes, the 2 camera locations are very close to each other. If we can relocate them, maybe we can capture more persons' positions in a better view. Another is since all the persons are standing on the ground and the Z coordinate of the foot is 0, we may be able to utilize the single view food projection to directly get the food location. That's all. Thanks for your listening.
Okay, thank you, Fan. Yes, thank you. Great presentation. So anyone has any questions?
Hey, Fan. I'm wondering, do you have a sense like why your online methods outperforms offline methods by a pretty large margin?
This is mainly due to when we try to make the single view tracking, we may make a lot of errors. Oh, sorry. Here, because we do not use appearance for the tracking compared to other vendors, actually we found the ID switch very quickly happen, and sometimes we can make this first step incorrect. And such kind of errors could be accumulated and affect the final results. That is, if we can get some final result, it is very good. But actually in the middle process, actually a lot of proper matchings already being rejected. Therefore, in our final offline, it's actually quite bad. But in our online cases, some errors may only happen within a sliding window. Even it can propagate, but its effect will be reduced as the sliding window keep moving on. Therefore, the single view tracking failures will have less impact and will get a little better result for the online case.
Okay, thanks.
Have I answered your question? Thanks.
Yeah, thanks.
Okay, we still have several minutes. So any other questions?
Hi, I have a question.
Yes, please.
So for the head bounding box detector, did you build a custom head detector or just use an available head box detector and train on this data set?
Just very simple one, use the yellow, and we do not spend too much time on it.
Okay, yeah, yellow V3 or V4?
We tried the yellow V4 and also yellow V5, but yeah, but actually it seems not too much difference.
Oh, okay. And for the COCO dataset head bounding box coordinates,
estimate like we get from the poses, but of course when we transfer the poses to the head bounding box, some bias or errors could be happen.
Oh, okay. So use the key points of the head to get a head bounding box location, right?
Yeah, exactly.
Okay, thank you.
Thanks for your question.
Okay, yeah, hi, Fan. I may have another question. It's related to your multi-frame optimization for the triangulation, right? You mentioned that could avoid a lot of errors. So, but here, for example, when you have this distance matrix, if you stack them together, it will become a tensor, right?
Yes.
So when you do the optimization, do you do, maybe you can give more details on how you do.
Here is, okay, to simplify it, actually it's a modified hierarchical clustering. So based on the distance, since here we don't know how many persons are there, we need non-parametric clustering. And for my personal preference, I also like hierarchical clustering, just like the first place solutions. And for the multi-views, we actually first to calculate each single view's distance. Oh, sorry, we'll accumulate the distance and then get an average. But also we also be aware of the maximal distance. If it's out of a certain threshold, we may reject it. And also we compare the mean of all the cross frame distance. Then in the end, we merge them together as a single matrix. Then we perform hierarchical clustering using the distance setting and threshold and get the final number and also the assignment.
Okay, so here maybe you are using a very small number of frames, right? Because do you assume that the number of person detected in each frame are consistent? For example, the size
actually,
right?
Maybe I suppose the ground truth of this data may be a 7% or 8%, but when I visualize the results, sometimes it's only for my situation, sometimes only have 5, sometimes it could be up to 10. So actually, I do not put in my framework due to the content too much information. I did a lot of refinement, maybe a little similar to the Alibaba Group's solutions, like merging the redundant checklists or like a connector broken checklists together. So such kind of refinements we may maximally alleviate the person's numbers issues.
Okay, thank you. Yeah.
Thanks.
Okay, if there's no more question, we can stop here. Thanks again, Fine.
Okay, thanks very much.
Let's have a 7 minutes break. We'll come back at 10:50 Seattle time. Thank you. Okay. Let's start the camera view winners. First speaker is from Hikvision Research Institute. Jie, can you share a screen?
Yeah, please wait a moment.
Okay, sure. Take your time.
Okay.
Yeah, we can see your screen now. Let's start. Thank you.
Okay. Thanks very well for listening my presentation about our method in the multi-camera, multiple people tracking challenge. If you have any questions, please feel free to interrupt me at any time. There are 5 main aspects to this topic: introduction, motivation, details of our proposed approaches, visualization results, and the summary. We will now come to the first part, introduction. Since the dataset has been introduced before, so I will just simply repeat our 2 tasks. The first task is to tracking the trajectory of the target point in the top-down view, which represents the position of the human body on the ground. That means each point of the ground truth is a foot point on the ground. And on the second task is to track the multi people in each camera. It seems similar to a normal multi-object tracking tasks. So let's move on the next slide and think about the challenges in the single camera tracking task. There are 2 main challenges, I think. The ID switches caused by the occlusion and long-term disappearance. So obviously, one solution is to use more cameras to cover different angles and also a larger field of view. So to reduce the possibility of occlusion and long-time disappearance. For example, if one person may be occluded by in one camera, but it can be also detected in another view. Also, if one person leaves one camera view and still in the other camera, so the track will be much easier. Thus, this problem becomes multi-target, multi-camera tracking, which is called MTMC. The usually way to in the multi-MTMC problem is to use appearance features to combine different trajectories, but there is also a difficulty. The appearance feature of the same target are usually different in different cameras. The possible reason includes different orientations, light condition, and background, and so on. So I think, if possible, in addition to appearance features, we still need another more reliable information. Here, I think the word coordinates by camera calibration is more reliable. Fortunately, in our MMP challenge, we have both multi-view cameras and also reliable global coordinates. So we decided to directly perform global tracking in the top-down view. This figure shows our proposed architecture. We follow the tracking by detection rule. First, propose the detection in the top-down view with the help of multi-view cameras, and then use some typical tracking algorithm to get the tracking results in the top-down view. That means we have 2 parts. The first part is multi-view detection, and the second part is typical tracking. And this is just a point tracking. And then we can convert the tracking results, return to the camera view. And for the first part, multi-view detection, there are some interesting works. In this paper, the author formulates the multi-view detection problem as a key point regression problem. Each key point represents one person. This is the output of this model. Each point means one person. And more specifically, they use the CNN network to extract features for each cameras at the same time. And then with the help of camera calibration, the entire feature map is directly mapped to the world coordinate system. That means we got this projected feature maps. This feature maps is not same to this feature map, but the height and width is similar to the occupy of this camera system. And then we just concate all the mapped feature maps together and perform the key point regression task. In this method, they just concate the feature maps in different cameras together, and in order to better integrate the features between different cameras, the author has made further achievements this year. They introduced the encoder structure in deformable DTR like this one to the multi-camera detection task, and we only need to modify the number of heights to the number of heights by number of cameras. We can get the feature map of all of the cameras and enable information interaction between each camera. About the details of this model, we can if you are interested, you can read this paper. It's very interesting. So we use the multi-view DTR to get the detection in top-down view. Like this. We got the we got the detection results in top-down view. Here, the bounding box is just for show. In fact, it's a point. And then the tracking becomes very simple. It can be seen from this picture. The distance between different objects are still far away compared with the MOT in camera view. This distance is much higher. So the occlusion between different targets is also significantly less. So even use the naive sort algorithm, we can also get a pretty good tracking. Of course, for better tracking results, we here still use the deep sort. So use Kalman filter for prediction, and this prediction is just for the point prediction, and Hungary algorithm matching. Of course, we also need the
I think there may be some issue with your slide. Your slide is still on the page, but it seems you are talking about something else. Right?
Let me share this again. Moment, why can't I? So let me reconnect the Zoom.
That's fine. Probably I can help you share screen.
But sorry, but I have modified a little in the.
Okay. Okay, we can see our screen now. Yeah. Hello, Jia. We cannot hear you.
Before, did you see this slide?
Okay, yeah, you can start now. Yeah, previously we didn't see this one. Yeah.
Okay, yeah, sorry. So the author introduced the structure of the encoder from a deformable DTR into this multi-view detection model to in order to better integrate the feature between different cameras, and the final results of this model is a feature map. It's just a feature map, and then we can use this model to get the detection results from the top-down view. And now we can see this one. This is this part is top-down view detection results. In fact, it's just a point here. The bounding box is just for better for show, and we can see compared with the MOT in camera view, the occlusion between the detection results is less. So even we use the naive sort algorithm, we can also get pretty good tracking results. So here I also use the deep sort. We use Kalman filter and Hungary algorithm to match, and also we need the appearance feature. Of course, we cannot get the meaningful feature appearance feature from this top-down view. So we need get the bounding box in the camera view. And also once we finish the tracking in the top-down view, we can convert this point to the camera view and get another subtract results. So let's see how to predict the bounding box in the camera view. With the help of camera calibration, we can easily convert the 3D coordinates in the space to the 2D coordinates. So we can easily get this blue point one. This blue point can just converts from the top-down detection results. And then we assume the person height is approximately 170 centimeter and get the green points one. And then we assume everyone stands in a square with a size of 50 centimeter, and we can get this right rectangle. Based on these 2 points and this rectangle, we can get a predicted bounding box. Of course, each person is different in height, and some people even sit on a stool or something others. So there will be errors in the bounding box we predicted. Therefore, we train another detection in camera view at the same time. And finally, we match the predicted bounding box, this one, and the detected bounding box with cascaded RCN model. We match them together and get the final bounding box in the camera view. With this bounding box in camera view, we can first get the reality feature, which is helpful for our deep sort algorithm, and also we can optimize our detection results. I will talk about this point later. And last, we can just easily transform the track results of top-down view to the camera view subtrack. So we get as I mentioned before, in the top-down view tracking is much easier than the top-down view, than the camera view. So now let's see how to optimize the detection results. The left figure means the detection results from the top-down view, and the right figures show the detection bounding box in camera view. By the previous method during matching, we can match them with algorithm with Hungary algorithm. These 3 bounding boxes are matched to the blue point, and these 2 bounding boxes are matched to the gray points. We can see sometimes there will be no gray bounding box in the first camera, it may be occluded or something, or some other reasons we don't care about it. And this is the final match results. And we can see there are no bounding box in camera view be matched to these black points. So we can think this black point is a false positive. We can just remove it and get the optimized detection results in top-down view. And then we just do the deep sort and and then transform it into the camera view. Now let's see some visualization results. In this sense, we can see the people occlude each other very seriously. If we use the typical MOT algorithm in the camera view, it will be hard. But in the top-down view, we can see the distance is still far, and so the tracking is much easier. And here, sometimes this green bounding box means it was not detected, but predicted by the Kalman filter. And sometimes when it over 30 frames not be detected, it will lost. And in this sign, we can see people are also occluded by many shelves, but by our method, they can also be good detected and tracked. The only problem is when sometimes people with special posture, for example, stoop or crouch like this one, it will be hard to be detected. But I think this problem can be solved by adding more training data. So to summarize, there are two important points in our method. The first is tracking in top-down view, and the second is trade-off between detection in camera view and top-down view. By this trade-off, we can get more specific detection results, and by this top-down view tracking method can easily get the final results. And we don't have any other post-processing or something others. And also, now we are still doing some research works in this dataset. We are trying to improve the generalization ability of this method. And also we are trying to train an end-to-end model for MMP tracking, but not more first detection and then tracking. Okay, that's all, and thank you very well.
Okay, thank you for the great presentation. So anyone has any questions?
I have a question.
Yeah, please.
So you project the features from the camera images to the ground. So what kind of feature did you project to the ground?
In fact, this is a feature maps get from the CNN network, and then we just how to say this.
So
for
what
example,
is
this
the CNN used for? For detection
it's
or
it's
for
just a
estimation?
ResNet. It's just a ResNet.
So what was the ResNet trained for?
It's trained for the key point regression. That means at the final we got this heat map, and the ground truth is just the if this point has a ground truth, it is once, and the other is 0, and we can add a Gaussian distribution and make them.
Okay. Do you mean that the CNN is trained for detecting fault points in the 2D images?
Yeah.
Okay, understand. So I have another question. So if we just focus on top-down view tracking, so your approach just looks somehow tedious. So so have you tried to just project the Real ID features, also project the Real ID features to the ground, and so we can just associate the detection results on the ground instead of projecting back to the 2D images and associated the 2D bounding boxes.
Okay, I have to say, in fact, in our method, the ready features is not important at all. So even we don't use Kalman filter, don't use a ready feature, we just use the naive sort. It can also get pretty good in MOTA, but a little.
So that sounds good.
Yeah,
that's cool.
Yeah.
That's cool.
So I think I didn't try, but I think if we just use the feature in this feature map, I think it also can also work.
Okay. Thank you.
Okay, thanks again, Jie. We are running out of time. If you have more questions, maybe you can contact Jie for more detail. Thanks again. Yeah.
Okay, thanks.
Next, we have Hongmin from AI team at Wiz Labs.
Yeah.
Multi-expert, multiple object tracking. So Hongmin, can you?
Yes. Yeah. Can you hear me?
Yeah, I can see your screen. I can hear you. Thank you. You can start.
Okay, sure. Yeah. Hello, everyone. My name is Hongmin Xu, and today I'm going to present our work, Multi-Expert Multiple Object Tracking in ICCV 2021 MMPT Challenge. Yeah, this work is with Zhongwei Chen, Xinyu Yuan, and Ling Chen. Yeah. Okay, this is the outline of this presentation. First of all, I will talk about the background of this work. Then I will mention some related works which we reference in our system. After that, I will illustrate the main concept of our proposed framework. Finally, I will show some experimental results and draw the conclusion. Yeah, why do we need multiple object tracking? Yeah, tracking can be applied to improve our daily life. For example, it can be used in the intelligent transportation system and for the camera surveillance. This is an example how tracking can be applied in a multi-target, multi-camera vehicle tracking system. And yeah, this is another example for the multi-target, multi-camera vehicle tracking system. So in this one, this is the overlapping perspective scenario. Yeah, you can see that the same identity are assigned the same ID in different cameras. And special thanks to Microsoft for organizing this challenge. Yeah, due to the privacy issue, there is no multi-camera, multi-people tracking dataset after Duke MTMT dataset is not available anymore. So this dataset including 5 different things. Here is an example from the MMPT official website for the industry safety case. Yeah, and this one is the retail store example. Yeah. Today, I will mainly focus on the camera view tracking system because we already heard so many incredible MMPT systems from the previous presentations. So and in order to design the camera view tracking system, there are some challenges need to be overcome in this track, such as occlusions, like in the camera view, there are like in the retail store, there are so many occlusions by all of the other people or the products. And also due to the unreliable detection, we also need to dealing with this kind of situation and the viewpoint variation. And sometimes the people or vehicle will frequently enter and exit the view very often. And also for the illumination condition, and also we need to dealing with the nonlinear motion, yeah, especially for the human tracking. So before we illustrate our proposed method, let's talk about the classical and the state-of-the-art approaches that we reference in our system. Now, the first one, yeah, just like the other things, I would like to mention is deep sort, which is the most well-known tracking by detection scheme for multiple object tracking. Basically, the deep sort need to do the detection first, then use the detected bounding boxes of each frame as the input to do the bounding box association along time. So the association operation is based on considering the IOU and the appearance similarity. Yeah, And after that, another important approach we reference is the JDE scheme, joint detection and embedding. This JDE framework is proposed in ECCP 2020 and was getting more and more popular now. Unlike tracking by detection is a separate detection and embedding framework, JDE aims to train the detector and embedding for data association at the same time. The other very similar scheme is a two-stage method that is very similar to SDE, separate detection and embedding. That is the only difference is that they use the feature maps of the detector as the input to train the embedding model instead of using the images. After the JDE is proposed, there is another JDE type of method called fair multi. Unlike the previous JDE using the bounding boxes for data association, fair multi adopts the center point of each identity for data association. According to this figure, you can see that using center points for tracking can reduce the occlusions during the tracking. So this is the pipeline of fair multi. Fair multi uses an encoder and decoder network as their backbone, and there are two heads, detection head and the reality head in fair multi, so that it can train the detector and the reality embedding at the same time. Once the reality embedding is trained, the reality embedding can be used for association to generate the final tracking results. Yeah, so here is our solution for camera view tracking. First of all, we use all the videos in the training stage. We use all the videos to train the general tracker. Then we train a network for the expert assignment purpose. So the whole idea is that we want to train multiple expert trackers for each different thing. Once we obtain the tracking results from these expert trackers, we can ensemble these results from these trackers to generate the final tracking results. Actually, in MMPT dataset, the scene labels of the training data, validation data, and testing data are already provided, so that we can just use the supervised learning to train a scene classifier for the expert assignment purpose. But in this challenge, since the scene label are already provided, so we directly exploit the provided scene information to do the expert assignment. But in order to build a more but in order to build a more general multi-expert, multi-object tracking framework, we still try to train a scene classifier for an expert assignment purpose. Here's the detail how we train the network for scene assignment. We use ResNet 50 as the backbone, and adding one ReLU layer, one average pooling layer, one FC layer, and one sigmoid layer to build a scene classifier. According to our experiments, we can obtain rank 1 accuracy about 99.95%, and so the expert assignment is doable in supervised learning. Moreover, we also try to use unsupervised way to generate the pseudo labels to train the expert assignment. By using the clustering algorithm, here we use the Gaussian mixture model. We can obtain the pseudo labels and then these pseudo labels can be refined by the annotators so that we still can train our expert assignment network. Yeah, here we try several cases for the GMM part. We try 3 and 5 and 10. Yeah, so turns out by generate the pseudo labels, no matter how many cases we use, that it can be simply refined by our scene annotator. And yeah, here is our final results on the MMPT report for camera view. You can see that there are over 60 teams in this challenge. So MMPT challenge is very popular competition comparing to the other ICCV challenges. And let's take a look about our ablation studies. Here we use the fair multi as our tracker in the proposed system. So fair multi is the baseline approach in our ablation studies. If we use the pre-trained model which is trained from the crowd human data set directly, we can achieve MOTA about 48%. And for the fair multi part, if we train on all the videos, and we can obtain like 74.6% MOTA. And if we only add one retail expert checker, which is only trained on the retail videos, and we can achieve like a 78.1% accuracy. And if we adding another industry expert checkers, we can improve the mota a little bit to achieve 78.4 accuracy. So finally, if we use all the expert checkers to generate our final result, we can obtain the mota about 80% accuracy. And yeah, here we show some of our qualitative results for the camera view checking. So it is only for the camera view checking. So the same identity in different cameras is assigned different IDs. So this is our results on the cafe shop scenario. And this one is for the safety scenario, industry safety scenario. You can see that we still can get pretty good result while the people are wearing similar clothing and they're also very close to each other. We can still achieve pretty good result. But yeah, we also try to generate the top-down view checking results. Yeah, here is our one demo for our top-down view checking part. So we didn't try to apply the 3D result project back to 2D to compensate. So yeah, our performance is not as good as the previous team. Yeah. So let's draw the conclusion. Yeah. First of all, multi-expert, multi-object checking is useful for no matter MMPT task or MOT task. And I think active learning is promising, which can be applied to generate more general multi-expert, multi-object checking framework. And our performance is achieved mota about 80%. Our final ranking for this challenge in terms of the camera view is number 2. Yeah, thank you.
Okay, thank you, Homi, for the presentation. So anyone has any questions?
Hello, can you hear me?
Yes.
So hi, Homi. So I was wondering that, so since you proposed a very interesting multi-expert work, do you think that it can be extended to like, not just sense difference, but can be extended to like even different camera view? Because I believe like if you can achieve better result based on different things, I think maybe camera view can also be integrated into the general multi-expert pipeline in yours works. Or do you think that's kind of like overkill for this topic? Yeah.
Yeah. The whole purpose of this kind of framework is try to do like a scene-aware multiple object checking, right? So it is very trivial that if we can for different model can dealing with different kind of environments. Yeah, so that's the whole purpose of this kind of framework. In terms of if you mention about overkill, yeah, it depends on your application. I think, yeah, if you try to use this kind of MMPT system in like, yeah, because it is very obvious that in industry scenario is pretty different to the coffee shop.
I see.
Yeah, so it's quite different, and it is also very obvious that the industry for this kind of specific purpose, like all the people wearing the very similar clothes, right? It is not reasonable to use the same re-ID or embedding model for these two different.
I see. Yeah, that makes sense. Yeah, thank you.
Yeah, no problem.
Thank you for answering.
So are there any other questions?
Okay, if there are no more questions, we can. Thanks again, Homi, for your presentation.
Yeah, thank you. No problem.
Okay, next let's have our last one in this track. Track 2, it's Zheng Yan from Information Processing Lab of UW. Zheng Yan, can
yeah, so can everybody see my screen?
Yeah, I can see your screen now. You can start. Thank you.
Okay, so let me start. So hi everyone. So I'm going to talk about our third place method of track camera view, and our methods called track-based multi-camera, multi-people tracking. And I'm Zheng Yan, and also call me Chris, and I'm working with Aotian, Zichen, Yuzhe, and we are advised by Professor Zheng Huang from University of Washington Information Processing Lab. So a little bit about us. So I'm a first year PhD student as well as Altian, and we are both working into the multi object tracking area. And I'm also interested in some of the 3D human pose estimation. And we are all working together in the information processing lab, and we are very interested in the multi-object tracking area. So our lab actually participated in lots of related competition, including the BMTT this year. So first, I'll briefly talk about our approach in this slide. We adopt a pretty standard two-step approach, namely doing the single camera tracking from each camera view at first, then conduct the multi-camera tracking by aggregating those tracking results from the previous step. We also put together a diagram for our workflow in the slide. As you can see in the red undercolor area, it's our single camera tracking. We first use Fair MLT framework to generate single camera tracking results, then use some naive short-term, long-term post-processing method to link those disconnect tracklet to enhance our performance. And then in the blue undercolor is our multiple camera tracking. Different from other participants, we try to get a foot point estimation from some key point RCNN and reproject them back to the real world coordinate to do an inter-camera tracklet association algorithm. And I'll go ahead and talk about our camera view track, and Altian will take over to talk about a top-down track. So we simply adapt a JDE framework, a Fair MLT, with some experimental modification on the model configuration to produce our single camera tracking result. We list some of those parameters we used for our experiment, and those slash numbers are different setting we use, and the underscore number is the one we found that performed the best on the testing server. And since Fair MLT achieved huge success on multiple MLT pedestrian tracking benchmark, we also used the pre-trained model and found that very useful to initiate our training. And so as previously discussed, there is some bias in the data set. So we also pay extra attention on those tracking parameters to prevent from exploding it. As you can see right here, we list out some of our tracking parameters for our final submission. So, and actually we also conduct some evaluation study using the validation set. And we found that by sort of like exploiting the list data sets bias, by lowering the maximum detection number or like a tracklet number or some of the value near the total number of people appearing in the data set, or given a very like long tracklet lifetime, we found that we can probably improve the MLTA from 0.73 to 0.8 and add IDF1 from 0.58 to 0.67 in the validation set. So yeah, so I think that's probably like a major concern for this data set, but I think overall this data set still works perfectly because as the previous presenter Homie mentioned, after Duke MD MNC, there's no public available multi-camera, multi-people tracking data set. So I think this data set still will benefit our research, yeah. And then, so our tracking association algorithm is also a standard, like a deep sort fashion. We use a Hungarian algorithm with calls based on the embedding similarity and bounding box IOU. After online tracking, we then do some post-processing using the method also developed by our lab, which won the BMTT challenge last year. We use a simple short-term retriever to compare the missing detection within 3 frames, and a long-term RID to compensate the occlusion problem by assuming the person will move with motion consistent and matching the RID features. But this did not work quite well. I mean, the long-term RID one, because so we think that the reason is probably because the MMB data set is a data set collected indoor, focusing on indoor scenarios, so that the people's motion is non-linear and very difficult to like predict with like linear maybe like projection or filter. So, and the MLT actually work quite well because they use they are recording sort of like a projection sense. So that's probably the main difference between these two data sets. So in our final submission, we did not include the long-term RID post-processing. Yeah. And this is some of our results. So as you can see, we try different settings, and these are all numbers recorded on a testing server. So actually in the last, I found our numbers actually very similar to what Homin did, because I think our backbone and Ola Star is very pretty similar setup. And the only difference that since we have at the very last stage of the competition, I actually also fine-tune on the retail set and found out there's a very slight improvement of the MLTA and IDF1. So I think that Homin's idea about a different thing, a more general approach to scene aware MMP solution is is quite interesting, and I think that will work if it's trained on different things. And yeah, as he mentioned, that for application purposes, if maybe we want to like track a certain like a store or something like a coffee shop, we can maybe have some data set label on those scene, and we can directly use this scene aware single camera tracking on those, and it will definitely improve the result a lot. Yeah, and this is the part for the camera track, and I will hand over to Altian. Oh, and this is some demo. Sorry.
All right. Yeah, can you hear me?
Yeah, we can hear.
Okay, great. Yeah, so I'll talk about our top-down view part. So to project our single camera tracking results to the top-down world coordinates, we need the focal point in the image coordinates for each detection. So to do that, we use two methods for estimating the focal point. First is using key point RCNN to directly regress the focal point from the image. And the key point RCNN performs human detection and also key point regression. Normally, there's it outputs 17 key points for human pose estimation, but for the purposes of this challenge, we only have one key point, which is the focal point. And so key point RCNN works well for people in full view, but people who are partially occluded, especially their lower half, may have no corresponding focal point output, or like a low confidence focal point from the key point RCNN. So to you can see that from the example image below, where the kind of four people at the forefront with the full view, you get it outputs we get a very good key point focal point detection. But then for the people in the back where they're partially occluded, they're either not detected by key point RCNN, or they are, but because of the occlusion, the focal point is not. The focal point confidence is very low, so it's not very reliable to use those. And in which case, we move on to the next method for getting the focal point, which is directly using the single camera tracking detection bounding box results, where we essentially, for each camera view, we define so for each camera view, we define an X and Y offset from the lower left corner of the bounding box as like the default focal point. And so we get this offset by basically taking the ground truth labels in the training set for each camera view, and then essentially getting the average of the X and Y offsets from all the different people in the image. And so this is so we use this default focal point when we can't really get a good focal point from our key point RCNN. And then in the next slide, given our image focal point coordinates, we can project each camera view tracking results to the top-down world coordinates using the provided calibration parameters. And in the top-down coordinates, we perform inter-camera track association using the following algorithm, where first we associate objects from two camera views frame by frame using the Hungarian algorithm with Euclidean distance as the cost. And then for overall track association, given two tracks like T1 and T2, they're associated if the number of frames where they are associated with each other in the frame by frame association divided by the length of either track is over some threshold, like maybe 0.5, then we would associate the two tracks together. And then finally, the associated tracks are then merged together using a weighted average. So in the next slide, please. Yeah, so the overall top-down tracking results are obtained from iteratively merging the single camera tracking results from different camera views together. So in this figure, W is the weight used in merging the associated tracks. And for this challenge, we don't merge all camera views. Instead, we use a select subset of the camera views based on the single camera tracking performance on the validation set and the degree of scene coverage. of the different camera views. And finally, in the next slide, we have a demo of 2 different camera views of the on the top row is the original single camera tracking results. On the bottom row is the corresponding multi-camera tracking results using this inter-camera track association, as well as the corresponding foot point for each track projected into the image. So our final top-down view results, we got a 0.82 for MOTA, which is a bit far from the top 4 results of like 0.96 and 0.93. I think the main reasons for this for the difference in performance is that one, we don't really perform any inter-camera re-ID, and also during the tracking process, the single camera tracking in each camera view is done independently, so we don't really take advantage of the multi-camera information. So that's all for my part on the multi-camera tracking.
Okay, thank you, Zhengyan and Tian. Yeah. Any questions? So maybe I have a question. So Tian, you just mentioned that when you do the key point estimation, you have first detect bounding box, then you regress the key point inside of the bounding box, right?
Right.
So does this improve your final performance? Because it seems to me that if this person occluded, the bounding box will be also kind of a partial bounding box, right? The foot point will be kind of outside of the bounding box. Right? So the foot point for those occluded person may still be inaccurate, right?
Yeah, correct. So
sorry, you can go first.
Oh yeah, so it does improve our performance, but you're correct that in the case of occlusion, it's still the bounding box would still not be a very reliable way to get the foot point, but I think it's more reliable than from the key points in the occluded cases, and also from our detection results with the for MOT, they also kind of do a better job of trying to fitting the bounding box to the whole profile, even if they're partially occluded.
Yeah, and so I want to add to that is because we also think of this problem during our deliberation of the competition, but in those ground truth labeling, we found out, especially in the retail scenario, even the people is like blocked by the shelves with only like they only had showing in the image, the ground truth still give like a whole body bounding box. So that's why we think that our method may still work, because you can see that even with all these heavy occluded things, our bounding box still give like a very a ratio like makes sense. So so I think that due to this labeling of the data set, so I think this method may somehow work. But if we are going back to other data sets, for example, like they only bound out those non-occluded part, I think this method will have some defect. Yeah, that's what I want to mention.
Okay, yeah, I understand. Yeah,
yeah.
Thank you. Yeah, because of the data set, they have full bounding box. Yeah.
Yeah.
Thank you. Yeah. Any other questions? Okay, if not, maybe thanks again for Zhengyan and Tian.
Thank you so much.
Thank you. So next, maybe Jiang, you can introduce our last keynote speaker.
Okay, sure. Yeah. So we have our final keynote talk from Dr. Hikvision. Hikvision is the semi-impaired innovation professor in the Department of Computer Science at Stony Brook University. Hi. His research interests include computer vision, augmented reality, medical image analysis, and human-computer interaction. And he had done a lot of wonderful work in the visual tracking field and won numerous awards. I'm not going to enumerate all of them. Today, he will talk about his recent work on benchmarking and diagnosis of visual tracking algorithms. So welcome, Haibin. Yeah.
Hello, everyone. Thanks for the introduction and also for inviting me here. So our group have been working on tracking for past maybe 12 or 13 years. So, but today I will mainly talking about benchmarks and some kind of recent diagnosis work we have done on tracking. Okay. So, okay. I will first give a very brief introduction about the tracking, kind of very brief one, and then we will talk about the tracking benchmark for generic single object tracking, and then I will introduce our recent tracking diagnosis toolbox named the Track Clinic, and then I will talk about benchmark for some special cases, and then multiple object tracking and other tracking cases. Okay. So yeah, a very brief kind of introduction about tracking. I think everyone knows already. Okay. So roughly speaking, we kind of view tracking as keep track of something across time. Okay. So depending on the definition of something, so we have different type of tracking. So the most, I think the most popular or the most widely studied tracking topic might be this something called generic single object tracking. Sometimes people call it as model-free single object tracking. So basically in the first frame, we somehow get either by detection or by manual annotation, get the bounding box of an object of interest. And then the goal is kind of localize this object in the bounding box across time. Okay. So it is called model-free because in this case, we don't assume prior knowledge about the category or about the object. Okay, this is a popular topic in visual tracking. And then there are also some type of tracking that is kind of, in terms of tracking accuracy, that's more precise. So one of the application in kind of widely in robotics and augmented reality is tracking some planar surface. For example, in the left, you can see that we want to track this planar surface, but very accurately, not kind of a axis aligned bounding box, but we want the exact surface. So this is widely used for robotics and augmented reality because with this accurate tracking, we can actually reversely calculate the pose of the camera. So therefore, sometimes people also call this as pose tracking, which means camera pose. Okay. So this is another type of tracking. So you can see compared to the SOT and in previous frame, this one can be more challenging because we need to determine the parameters of the surface, so it needs more parameters. Okay. So along this line, things can be more complicated. For example, if we want to track something like a deformable object, in this case, in the left and right, we have two kind of linear or multilinear structures. So in the left, we want to track this, the 3D points of the skeletons in a depth image, depth video. And on the right-hand side, so we're interested in tracking the deformable curvilinear structures. So in this case, is a guide wire in a medical imaging scenario. So in this case, the dimension of the slit space is much higher. Okay. So we can make this even more complicated. Suppose we want to track a deformable surface. Okay, sometimes if there's occlusion, so that will make things even more harder. Okay. So, and then along the other dimension, so instead of tracking one object, so sometimes people are interested in tracking multiple objects. So which is actually the whole workshop today about. Okay, but we only studied the things for single object cases. Okay, so these are the multiple object tracking, and there's some also kind of extreme case we would say for visual tracking. So this is something like SLAM or structure from view thing. So I view this as a tracking problem because in some sense, in this problem, we are interested in localize the camera pose and essentially everything in the same across time. So this is why this problem becomes extremely hard. So all these, in my opinion, are different type of tracking problems. So basically tracking something across time. Okay. So apparently, I mean, after starting all these tracking problems, we consistently facing the problem of benchmark or dataset problem. So that motivated us to compile several kind of benchmark datasets. Okay, so that's a major topic for today's talk. Okay, first let's talk about the generic single object tracking benchmarks. Okay. So the evaluation, I mean, in the old days, I mean, for single object tracking is relatively simple, especially before 2013. So typically, the data set contains only a few sequences, and so the problem is that it's hard to reflect the generalization capability of different trackers, and also by that time, the trackers often have many different parameters. So it's quite easy actually to overfit a tracking algorithm on kind of manually selected data set. At that time, data set means 5 or 6 and at most like 20 something sequences. Okay, so in fact, I mean, to address this issue in 2013, we actually published a paper. Personally, I think this is a very interesting paper. To talk about the subjective bias in the tracking evaluation. This paper, to my knowledge, might be the only paper I mean, in computer vision without running any computer vision algorithms. I'm not the tracking algorithm at all. So the idea is, okay, in the past, we have a lot of tracking algorithms by that time, I mean, tracking tables, but they all are kind of limited to evaluate on a few kind of sequences. So therefore, the authors they usually have some bias, and that is understandable, which was also true for papers from my group, to be frank. Okay, but there's no much, I mean, kind of subjective bias when we compare with other methods. So basically, suppose our method is method A. Basically, we want A to be better than other methods like B and C. But to be frank, we don't really care, or we don't really pay too much attention between the ranking of method B and C, because anyway, they are none of them are from our group. So therefore, the comparison between method B and C are relatively objective. Okay, so it's like in a kind of sport tournament. So basically, okay, so we can view each tracker as just an athlete in a match. So then we were based on their comparison in different paper and different match to calculate a score. So finally, we used all the scores. Essentially, we collected all the papers in the past 10 years and calculated statistics. That's what we did in this paper. Therefore, we didn't run any tracking algorithms. But anyway, this is before 2013. But after 2013, things changed. Okay, so let's first say kind of roughly mention the motivation why we need benchmarks and dataset. Okay, so basically the large dataset are needed. I mean, essentially for the statistical significance, right? And also with large dataset, we can have some diversity. I mean, reliability for generic of tracking for different categories or different challenging factors, hopefully. Okay, and also due to especially due to the popularity of learning, especially deep learning based trackers. So we also need a large and hopefully annotated database, a data set for training. Okay. So then, as I said, things changed since 2013. Was first, due to the tracking benchmark by Minshuan's group in CVPR 2013. This object tracking benchmark with 50 sequences, and then people realized the importance. And then there's a lot of different tracking benchmarks presented, and after that, okay, those benchmarks largely boost the performance of trackers and the development of tracking algorithms. Okay. However, I mean, there are still some issues with this benchmark. First, they are still relatively of small scale. Okay, so for example, if we want to compare a tracking benchmark with like ImageNet, right? We know that the ImageNet contains, and for the popular version, contains about 1 million images, right? But for tracking, roughly speaking, we can only treat one sequence as one sample. Okay, so but typically all tracking benchmarks mostly have only like 100 and 200 sequences. So the number is very, very small compared to other domains, especially like image recognition. Okay, and also I mean a lot of previous tracking benchmarks, I mean the sequence are short term. So the one issue with short term is that it usually involves less complicated cases. So it involves less number of challenging factors. Okay, and also another issue is about the category bias. So due to the collection process, typically some category has a lot of sequences, but not all. But some categories has only a few like that. Okay, and also we need high quality annotation. Okay. And one more thing is about language description, because the vision in the language thing only got popular recently, but for the tracking benchmark, there was no language description before. Okay, so there's a few kind of exceptions, like recently proposed large scale benchmark, like TrackingNet and Oxford UVA. Both of them have actually large benchmarks. But for these two benchmarks, the annotation is kind of not high quality. Either I mean like every 30 frames, or they are labeled by tracking algorithms, so which theoretically cannot guarantee the correctness of the ground truth. Okay. So another one is the GOT10K, so by Kaichi's group. So that one contains 10,000 videos and 1.5 million frames. That one is close to ours. So okay. So in the chart here, so we see kind of those statistics of these benchmarks. So roughly speaking, the y-axis is the average video length. The x-axis is the number of videos. The size of the pie corresponding to the number of frames. So we proposed the so-called La Sorte, which is by far the largest public one. Okay. So then we were talking about this benchmark is large scale single object tracking. Okay, it was kind of annotated by Hardly and by a lot of my PhD students and of my collaborators. Okay. So these are some detailed statistics and the comparison with previous ones. Some highlight are here. So first we are kind of large scale. We have 1,550 sequences and 3.87 million frames, and with high quality annotation. By high quality annotation, I mean actually each frame will be annotated at least once and double checked at least once. So to make sure the high quality. And also to deal with the diversity, we first select kind of 85 categories, and then we kind of balance all these categories with 20 sequences for each category, so that we won't have bias towards certain category. And also they are long-term, so basically the average length of each sequence is 2,500, and actually the minimum length is 2,000, still long-term. Oh, by the way, I think in terms of long-term tracking, somehow people kind of agree that with more than 1,000 frames, we can view that as a long-term tracking. And there's no rigorous definition, but somehow people decided so. Okay. And also for each each sequence, we provide some brief language description. Okay. So here's some thumbnails of all these sequences, and here's our examples for the language description. So for the first one, we say, okay, it's white bear walking on grass around the riverbank. So this one, we already see some recent work using this benchmark, try to connect the language description and the video sequence and the tracking. Okay. So for evaluation, we don't actually have kind of limitations of different protocols because we released our data. We didn't reserve anything, any annotations. So we suggest two types of protocols. The first one we call the full overlap protocols. In this case, we use 70 categories. In total, we have 85. Okay. For these 70 categories, for each category, we have 16 sequences for training and 4 sequences for testing. So altogether, we have a little bit over 1,000 for training and the rest 280 for testing. Okay. Another protocol we call it as one-shot protocol, which means we use all the sequences from all the 70 categories. Altogether, there are 1,400 sequences as training samples. And then we use all sequences from the 15 unseen categories for testing. Okay, so therefore we formulate this one-shot protocol. I want to emphasize here that these 15 unseen categories and these categories are carefully selected. So basically, when we determine these categories, we purposely select something which has not appeared in previous tracking benchmarks, and furthermore, which has not appeared in ImageNet. So therefore, to reduce, we tried our best to reduce the potential knowledge of tracking algorithms about these categories. Okay. So in our ITCV version of the paper, we kind of tested altogether 48 classical and state-of-the-art tracking algorithms. So, and all these benchmarks and these results can be found in our website. Okay. So this is about the generic single orbit tracking. Okay. And the next one, we're talking about the kind of diagnosis. So we know that tracking is very challenging because there's many challenging factors like out of view, occlusion, illumination change, deformation, blur, and background clutter, etc. Okay. So in fact, in many previous tracking benchmarks, I think currently is kind of the de facto and kind of requirement for a tracking benchmark. They were always annotated for each sequence the type of challenging factor involved. Okay. So like in this case, in this sequence, they will say, okay, this sequence involves shape variation and occlusion. Although there's no annotation for the location of shape variation and occlusion. The color is just provided by us for visualization. Okay. So basically, existing benchmarks, they mainly focus on kind of evaluating the global and performance of the tracking algorithms. Okay, they have per sequence attribute. Okay, but this may not be accurate for kind of analyze the tracking performance with respect to different charting factors. Okay, first, it's hard to localize accurately the failure frames because we don't know the failure, whether the failure relates to specific challenge factors. Okay, and furthermore, it's hard to disentangle multiple challenge factors. For example, in this example, okay, if we have a tracker that failed for shape variation, okay, but because shape variation actually happens before occlusion in this sequence, so we will make conclusion that this tracker is also sensitive to occlusion. So which may not be true because it does not get a chance to work on the occlusion cases. Okay, so therefore this kind of evaluation might not be reliable enough for certain challenge factors. Okay. So based on this motivation, we think maybe a very nice and kind of tracking diagonals dataset should contain sequence with two properties. The first is purity. So we hope that each sequence should contain one and only one challenge factors, one major challenge factor, let's say. So that the performance, if we know that okay, a tracker fails on certain sequence, we know exactly what challenge factors it is affect to. Okay, so and then of course for each sequence we should also have a few number of kind of easy frames so that the tracker can be stabilized. Okay. And in this sense, we feel that we don't necessarily need a long sequence. Okay, previously, I mean, a lot of tracking benchmarks, they focus or they emphasize on long-term tracking sequence because that's kind of more challenging. But for diagonals, we think maybe short one might be even better because on the short one with one and only one challenge factors, so it's easy for diagonals. And of course, short sequences will also provide the benefit of running time efficiency. Okay. And the second requirement is about the quantity. So basically, we want and for each challenge factor, we want a decent number of videos so that we can draw the conclusion with statistical meaningless. So in our case, we use 30 as the minimum one. Okay. So with these ideas, we propose kind of a tracking kind of diagonals platform or toolbox and whatever you can call it. Okay, we call it a track clinic. So what we did is first we extract from these three benchmarks, 460 sequences, the original video. Okay, and then we annotate every frame of these videos with challenge factors. And basically frame-wise annotation of challenge factors. Okay. Once we've done this, we can just create a lot of short clips as we described in this slide. So each short clip should contain a few kind of easy frames followed by one and only one challenge factors. Okay. So with this together, we collect a new data set. So we work for 9 different challenge factors. 2 of them are kind of single challenge factors. 7 are single challenge factors, and 2 of them are compound factors. Okay, so these are the factors. So single factors including occlusion, rotation, out of view, background clutter, illumination variation, motion blur, and the shape variation. And the challenge compound factors include occlusion, background clutter, and the occlusion and the rotation. We use compound factor because those 2 factors quite often they just happen together in the same frames. Okay, so therefore we combine them together. Okay. So here are the statistics. So altogether we got more than close to 2,400 short kind of tracking clips. Remember that, okay, each sequence from the original tracking benchmark can actually generate more than 1 clips because as we mentioned, each sequence, especially the long sequence, they may involve actually a few different types of challenge factors. So we can decompose them. Okay. So then we also provide kind of some systematic evaluation toolbox. So basically you can run your algorithm using our toolbox, and then we can generate all these kind of reports for you. Okay, so here's our example when we use DIMP, a popular tracking algorithm. So we can generate the kind of number of failure cases with respect to different challenge factors here, and also different consistent analysis table. And we also provide the kind of comparison for different trackers. Using this chart. So one interesting thing from this table, this figure, we can see is that most of the state-of-the-art kind of tracking algorithm, it seems that most of them are not sensitive to illumination variation anymore. So in the past, I still remember in the old days, there's still some papers on. There were some papers on addressing the illumination issue. So you can see that actually currently most of the state-of-the-art tracking, they are kind of perform close to saturation, with respect to illumination. So therefore, in some sense, illumination is not challenging anymore for tracking algorithms. Okay, and the most challenging part is out of view. So basically, you can say most of them performs the worst on out of view cases. Okay, so and you can say you can use this chat to analyze other charting factors as well. Okay, so this is for diagnosis. Okay, so okay, we'll move to for another special case we recently got interested. Okay, so basically in robotics and also human machine interaction, so we quite often need to deal with transparent objects. Okay, so to track this, these objects are kind of very challenging. So because they are transparent, so essentially means their appearance is very unreliable because it has some appearance from the background. Okay, so and currently, I mean, there's we didn't see any much kind of significant work on tracking along this line, neither the tracking algorithms or the tracking benchmark. Okay, so because of this, we decided to collect our own data set, and for this purpose, this paper actually was just presented in ICCV. Okay, so here are kind of some example videos we collected, and most of them, I think, yeah, most of them collected from YouTube. Some of them maybe from Youku and some video sharing website. Okay, so here are some statistics. Yeah, we first determined 15 object categories, and then we use 15 sequences per category. So therefore, we have a very well balanced data set. Okay, so here are some statistics. We have the number of videos, 225, and total frame are about 68K, and it's not long term, but yeah, middle sized. Okay, and we also have a number of attributes annotated, attribute for 15 different attributes for at sequence level. Okay, and because there was no previous method and tracking algorithm focused on transparent objects, so we design a kind of a benchmark, a baseline one. What we did is that we kind of improve the popular algorithm Atom with a recently proposed transparent object segmentation algorithm. Okay, essentially, we use a feature from this transparent object segmentation. We use that feature and merge that into the Atom tracking algorithm. So this is Atom, and this is a proposed one. We call it the trans Atom. So basically, we have a new kind of feature which hopefully will capture transparency information, and then we get a new baseline. Okay. So here are examples on the quantitative example on the benchmark. We can see that the transparency branch did help the tracking algorithms. Okay, although we didn't really do much along this line, we just say, okay, we have some pattern as a baseline. We just improve that with the existing transparency feature. We can still see the improvement. So in the future, we hope to see more kind of dedicated algorithm for this transparent object tracking. Okay. Next about multiple object tracking. So we know that multiple object tracking is popular, apparently already knows, okay, a very popular topic. Okay, so these are some results from our recent work. And current MOT benchmarks mostly focus on some just a few previous known categories, especially like people, vehicles, human face, and also sometimes in specific domain like in cell tracking, they focus on cells. So in all this case, the algorithms heavily rely on the detection. So basically, typically people use some offline tuned detector or maybe an online tuned detector for these algorithms. Okay. So, but by contrast, this generic multiple object tracking is less studied. There are, I think, a few papers before, but apparently, we face the same problem. There's no decent benchmark for this one. Okay. So addressing this problem, this year, 3PR, we proposed a new tracking benchmark. We call it as GMOT40, so which contains apparently 40 sequences. Okay. So here are some examples. So what we did is that we first we determined the 40 categories, and then for each category we found the 4 videos from internet and manually annotated all of them, right? And that's the basic thing. The average length is 240. Okay, so this is benchmark, and then for baseline algorithms. So again, and for this one, there's not many tracking algorithms dealing with this before. So we kind of adopted several existing tracking algorithms, but those algorithms were not originally designed for generic MOT, but we just adopt them and with some simple adaptation, just to provide the benchmark analysis. Okay, so including the MDP, kind of a very classical one, and the deep sort and the IOU tracker and the FarmNet, which was from my own group. So you can say these are the results. So it's it's still far from saturation. So I think there's a lot of things can be done along this line. Okay, so the website is here. Okay. And finally, I will briefly introduce a few other tracking benchmarks we proposed recently. The first one is for the 2D tracking in augmented reality, for example. I think I already mentioned this beginning. Okay, so previously there are a few benchmarks for this proposed, but I think that they are either kind of in and both of them I think in lab environment with special devices, so which makes them less practical to evaluate the real performance. Okay, so to addressing this issue, we proposed a kind of a tracking benchmark kind of in wide. So basically, we manually, we collected we determined the 30 different planar objects in the real life. We just my students, they just go outside to find different planar things. So luckily, we found that there are actually a lot of such planar surfaces. Okay, and then for each of them, we use cell phone to capture these videos to simulate the real practical issues. Okay, and then we have 7 different scenarios, like zoom in plane rotation, out of plane rotation. We have 7 different cases. So therefore, altogether, the data set has 210 sequences. So basically 30 objects by 10 different camera motion. Okay. So one particular thing I want to emphasize is about handling the missing part and for this annotation, because as I mentioned, this tracking we need much higher precision than typical SOT because we need the tight bounding box. Okay. So in this case, this one is represented by, we use 8 control points to represent each bounding box. It's 4 corners and 4 middle points. Okay, so we need the middle points mainly to dealing with this missing part. Like in this case, we have occlusion. So if we have occlusion, we still have some points here, and based on the visible points, we can interpolate the missing part. And also the same thing happens to out of view. Okay, of course, we assume that at least in terms of the area, half of the objects should be visible. Otherwise, even this annotation can have problems. Okay, but you can see why this is challenging. Okay, so this is this planar surface tracking benchmark, and here are some kind of statistics I already mentioned. I will ignore that for now. Okay. So, and recently we also proposed a kind of a small tracking benchmark for surface tracking. And this is a paper we published in ICCV 2019. The main reason we propose this benchmark is mainly because we are interested in tracking this kind of deformal surface. And there were a few papers before, and we kind of apparently want to use the data set in previous papers, but we found out, we actually contacted all the authors before. And unfortunately, most of the data set used in previous papers are either missing or the annotation is missing. So we actually only got a few of them, I think 2 or maybe 3, and from previous people. Somehow they are missing. So then we decided to just kind of build our own data set, which is again non-trivial. So what we did is essentially we use a Kinect sensor. We collected, we used 11 different surfaces. And then we use Kinect sensor to roughly estimate its depth. And then we manually correct or annotate all these landmark points on the surface. Okay. So altogether we have 11 video streams and more than 3,000 frames. The object we used contains 7 printed pictures, 2 newspapers, and 2 cushions. Okay. So these are the benchmarks. Here are 2 examples with kind of surfaces. So you may feel that these benchmark are kind of these sequences are kind of relatively simple. These actually are real tracking performance and from our algorithm. You can see still we still miss from time to time. Okay. But the problem, this is kind of far from in the wild. It's still kind of like lab based, but I would say this is kind of still the art in the wild case. Okay, so there's a lot of things to be done along this line. And finally, I also recently got involved in this UAV tracking challenging and the benchmark thing. So we call it as Hikvision. So it contains a lot of videos captured at different cities and are very dense and rich annotations for different objects like vehicles, pedestrians, and so on. Okay, these are large benchmark. It's not only for tracking, but also for detection and static detection and video detection. Okay, so these are the UAV things. Okay, I think I'm done with introduce this. So to conclude, so in this talk, I first briefly talked about the tracking problems. And then I presented our recent work on single orbit tracking benchmark, the short benchmark, and we presented the track clinic kind of platform so that you can use that to evaluate the performance with respect to specific challenge factors. Actually, you can also use this to train if you want to. You want your tracker to be robust to a certain challenge factors. You can use this benchmark to train that. Okay, and we also proposed a benchmark for transparent orbit tracking, and for generic orbit tracking, multiple orbit tracking, and the tracking benchmark for special cases like zoom-based video and deformable surface and the planar surfaces. Okay, so yeah, that's all. Yeah, I want to thank you all my students, my collaborators, and also funding support for this work. And also thank you for being with me for the talk. Thanks.
Yeah, thank you. This is really an impressive set of the data set.
Mm-hmm. Oh, by the way, this set can be found here. There's a link for all this benchmark. Yeah, sorry for that.
Okay, good. Any questions?
I have one question. Thanks for the nice talk. You mentioned this one fact, the challenge factor. I think the biggest one is OV, all the view. I wonder is that the one where a person walks out of the view and then comes back? Is that the one, or is it partially also out of view?
For that one is out and back, exist and back, because we do have occlusion. That's another challenge factor. So that one is kind of part of it. So okay. A typical example, I think we have a video like some people is playing with a football and they out of view and go back. So yeah.
I see. So that's really, it's kind of like a re-ID issue.
Yeah, that's like a re-ID in people tracking. Yeah.
Okay. What's the second worst? I didn't see you have a didn't see the second worst one.
I think it's
the occlusion. You think it's occlusion?
No, that's a shape variation, but that one is a little ambiguous. I think not really. Okay, shape variation.
Shape variation.
Shape variation is also bad thing. But here for shape variation is actually kind of we combine scale change and the kind of some kind of rotation, we combine it together. Yeah, because it's hard to tell whether this one is scale change or maybe the object actually expand itself. So we kind of combine this together as shape variation. Yeah.
I see. Okay. The one on the right most, that does not look that good either. That's what's that?
I think it's occlusion and the rotation. I think that's
occlusion and rotation.
Occlusion is combined one. Yeah.
Okay.
So this means the occlusion happened also with rotation. So like like this one. Okay. So occlusion and rotation. Yeah. For my face. Yeah.
I see. Okay. Thank you.
Okay, so actually we are almost out of time. Yeah, this actually is the last session of our current workshop. So yeah, so I think we can conclude our workshop now. Okay, thank you everyone for attending.
Okay, thank you. Yeah, thanks everyone. Thank you.
Yeah, thanks.
Thank you.
Okay.
Hey, bye.
Thank you. Bye.
Thank you. Bye.